tensilistic requirements. Right now, as you prepare for sleep, 8 billion people share this planet with you. 6 billion of them have never seen the Milky Way. They have never witnessed the pale river of light that arcs across the night sky, the combined glow of hundreds of billions of stars that form our galaxy's spiral arms. They cannot see what every human being who ever lived saw each night until roughly 1 century ago. The stars have not disappeared. We have simply made them invisible. In June 2016, a team of researchers led by Italian astronomer Fabio Falci published the New World Atlas of Artificial Night Sky Brightness in the journal Science Advances. The study combined high-resolution satellite data measuring Earth's nighttime light emissions with precise sky brightness measurements taken from thousands of locations worldwide. The numbers were staggering. 83% of the global population lives under light-polluted skies. In the United States and Europe, that figure rises to 99%. 1/3 of humanity cannot see the Milky Way from their homes, even on the clearest, darkest night of the year. In countries like Singapore, Kuwait, and Qatar, 100% of the population has lost the night sky. The light we created to push back darkness has erased one of the most fundamental human experiences. This should not be possible at cosmic scales. The Milky Way stretches across 100,000 light-years of space and contains between 200 billion and 400 billion stars. From Earth, we sit roughly 26,000 light-years from the galactic center, embedded in one of the spiral arms. On a truly dark night far from artificial light, the Milky Way appears as a luminous band spanning the entire sky from horizon to horizon. Ancient cultures built their mythologies around it. The Greeks saw spilled milk from the goddess Hera. The Romans called it the Via Lactea, the Milky Road. Hindus described it as the Akash Ganga, the Ganges of the sky. Aboriginal Australians saw not the light, but the dark dust lanes as sacred symbols. For nearly all of human history, this celestial river served as humanity's nighttime companion, a reminder of our place in something vast and old. Then, in the span of just 5 generations, we made it vanish for most of our species. The mechanism is straightforward, but the scale is unprecedented. Artificial light from cities, suburbs, streets, buildings, parking lots, and outdoor advertising scatters in Earth's atmosphere. Molecules of nitrogen and oxygen, along with water vapor, dust, and aerosol particles, redirect this light in all directions through a process called Rayleigh scattering. The same physics that makes Earth's sky blue during the day makes it glow at night under city lights. This scattered light creates what astronomers call sky glow, a diffuse luminous veil that fills the night sky with a faint orange, yellow, or blue-white haze depending on the type of lights used. Sky glow drowns out faint celestial objects the way city sounds drown out distant whispers. The stars are still there, still shining with the same intensity they always have. We simply cannot see them through the artificial twilight we have created. Astronomers measure light pollution using the Bortle scale, developed by amateur astronomer John Bortle in 2001. The scale runs from Class 1, excellent dark skies where the Milky Way casts visible shadows and zodiacal light spans the entire sky, to Class 9, inner city skies where only the moon, planets, and the very brightest stars penetrate the overwhelming artificial glow. In a Class 1 location, you can see roughly 5,000 individual stars with the naked eye and observe galaxies, nebulae, and star clusters with stunning clarity. In a Class 9 environment, you might see fewer than 50 stars total, and the concept of the Milky Way becomes abstract rather than experiential. Most urban dwellers now live permanently in Class 7 to Class 9 conditions. They experience night not as darkness, but as a kind of perpetual dim twilight, never truly dark, never truly revealing the universe beyond. The growth rate makes this exponentially worse. Global artificial light emissions increase by approximately 2% per year, a rate that appears small but compounds dramatically over time. Between 2012 and 2016, satellite measurements from the Suomi NPP satellite's visible infrared imaging radiometer suite showed that artificially lit outdoor areas grew by more than 2% annually, while the brightness of already lit areas increased by more than 2% as well. This creates a doubling effect. Not only are we lighting new areas that were previously dark, we are also making already bright areas even brighter. At this rate, a child born today in a moderately light-polluted area will experience night skies 50% brighter by the time they reach 30 years old. The universe is disappearing not in a sudden catastrophe, but in a gradual brightening that most people barely notice year to year. The transition to LED lighting accelerates this trend in unexpected ways. LEDs are more energy efficient than older sodium vapor or mercury vapor lamps, which should reduce light pollution by using less total energy for the same illumination. But economics and human behavior work against this potential benefit. Because LEDs cost less to operate, cities and businesses install more lights than before, a phenomenon economists call the rebound effect. The money saved on electricity gets spent on additional lighting. Furthermore, early LED streetlights emit significantly more blue wavelength light than older yellow sodium lamps. Blue light scatters more efficiently in the atmosphere than red or yellow light, roughly 4 times more efficiently according to Rayleigh scattering physics. This means LED streetlights can produce up to 2.5 times more sky glow per unit of light emitted compared to the older lamps they replace. Cities switching to LEDs with the intention of reducing light pollution often inadvertently make it worse. Scientists confirm the extent of this transformation through multiple independent methods. Ground-based measurements using specialized photometers that record sky brightness at precise wavelengths provided detailed local data. The Dark Sky Meter smartphone application, developed by astronomers and used by thousands of citizen scientists worldwide, collected millions of sky brightness measurements from diverse locations. Satellite imagery from NASA's Suomi NPP satellite and the Defense Meteorological Satellite Program captured nighttime light emissions with unprecedented resolution and sensitivity. All 3 approaches converged on the same conclusion. Earth's night sky grows brighter every year across nearly every inhabited region of the planet. The exceptions are rare and remarkable. A few isolated areas in central Australia, the interior of Greenland, portions of the Sahara Desert, and small regions of the Amazon rainforest still preserve truly dark skies. For most of humanity, these places are unreachable. Think about that for a moment. We have fundamentally altered one of the most basic human sensory experiences, the appearance of the night sky, across most of the planet in less than 100 years. Someone born in 1920 in what would become suburban Chicago grew up seeing the Milky Way every clear night from their backyard. By 1970, it was gone from that same location, washed out by the growing sprawl of sodium vapor streetlights and illuminated shopping centers. By 2020, you would need to drive more than 300 miles from Chicago to find skies dark enough to see the Milky Way clearly. This represents a complete transformation of the human relationship with the cosmos, faster than any previous change in our evolutionary history. For 300,000 years, Homo sapiens looked up and saw roughly the same night sky. In 3 generations, we erased it. The loss extends beyond simple aesthetics. Exposure to natural darkness regulates human circadian rhythms through the production of melatonin, a hormone that controls sleep-wake cycles and provides antioxidant effects. Bright light at night, particularly blue wavelength light from LEDs, suppresses melatonin production and disrupts circadian timing. Epidemiological studies link chronic light exposure at night with increased risks of sleep disorders, depression, obesity, diabetes, and certain cancers. The World Health Organization's International Agency for Research on Cancer classified overnight shift work involving circadian disruption as a probable human carcinogen in 2007. While shift work involves more than light exposure, the disruption of natural light-dark cycles appears central to the health effects. Entire populations now experience low-level circadian disruption simply from living in perpetually bright, nighttime environments. Ecological impacts cascade through ecosystems in ways we are only beginning to understand. Insects, which evolved for hundreds of millions of years under natural darkness, exhibit fatal attraction to artificial lights. Moths, beetles, mayflies, and other nocturnal insects circle streetlights until exhaustion or predation kills them. Recent studies suggest that artificial light may be a significant factor in the worldwide decline of insect populations, which have decreased by more than 75% in some protected areas over the past 3 decades. Migratory birds, which navigate partially by stars, become disoriented in brightly lit cities. During peak migration periods, hundreds of thousands of birds die annually from collisions with illuminated buildings in North America alone. Sea turtles, which rely on darkness to locate nesting beaches, and the reflection of starlight on ocean water to guide hatchlings to the sea, increasingly fail to reproduce near developed coastlines. Fireflies, whose bioluminescent mating displays depend on darkness, vanish from light-polluted areas. The night has always been a distinct ecological realm with its own communities of species adapted to darkness. We are flooding that realm with light, and the species that depended on it have nowhere to go. Before you drift off, leave a comment. What time is it, where you are right now, and where in the world are you watching from? Professional astronomy suffers profound impacts as well. Every major optical telescope built before 1980 has watched the sky above it grow progressively brighter. Palomar Observatory, which housed the world's largest telescope when it opened in 1949 on a remote mountain 100 miles from Los Angeles, now operates under skies degraded by light from cities that have grown dramatically in the intervening decades. Mount Wilson Observatory, where Edwin Hubble discovered the expansion of the universe in the Ejewos, barely functions for serious research anymore due to light from the Los Angeles basin below. Modern telescopes must be built in increasingly remote locations, deserts, mountaintops in Chile or Hawaii, isolated islands. Even there, satellite mega-constellations like SpaceX's Starlink are beginning to streak through long exposure images, creating new forms of light pollution from orbit. Humanity's window to the universe narrows as our lights brighten, but perhaps the deepest loss is cultural and psychological, harder to quantify, but no less real. For all of human history until recently, every person experienced awe at the night sky. They saw evidence of vastness beyond human scale. They wondered about their place in the cosmos. The stars provoked questions about origins and endings, meaning and meaninglessness, whether we are alone. These questions emerged naturally from direct sensory experience of the night sky, not from books or screens, but from simply looking up. Now, most people must make a deliberate journey, driving hours from cities, hiking to remote locations, just to see what their ancestors saw every night. The universe has become something you must seek rather than something that surrounds you. This represents a disconnection from nature as profound as the loss of wilderness, or the extinction of familiar species. We have built walls of light around ourselves, and in doing so separated ourselves from the cosmos that made us. The physics ensures this will only grow worse without intervention. Light pollution follows an inverse square law in one direction, but spreads widely through scattering. A single bright light source impacts sky brightness across hundreds of square kilometers. This means individual action provides limited help. Installing motion sensors on your porch light makes no measurable difference if your city installs 40,000 LED streetlights the same year. Light pollution functions as a tragedy of the commons, where individual rational choices, like installing security lighting, create collective harm that affects everyone. Breaking this cycle requires coordinated policy changes, building codes that mandate shielded lighting, regulations on light intensity and hours of operation, public awareness of the problem. Some communities have begun implementing dark sky ordinances. The International Dark Sky Association certifies dark sky places where natural darkness is protected. But these remain rare exceptions. The overwhelming trend is toward more light, brighter light, ever-expanding light, eating away at the darkness that remains. The Milky Way is still there, arcing across the sky as it has for billions of years. The photons from those hundreds of billions of stars still travel through space, crossing millions and billions of light years to reach Earth. They arrive here carrying information about stellar ages, chemical compositions, distances, motions. They pass through our atmosphere and they pass through the shells of scattered artificial light we have created. Then they reach our eyes too dimmed, too overwhelmed by local brightness for our retinas to detect. We have not changed the universe. We have changed what we can see of it. The question is whether we will choose to reclaim the night sky or whether future generations will know the Milky Way only as words and images. The mechanism that steals the stars operates on principles established more than a century before anyone recognized light pollution as a problem. In 1871, British physicist Lord Rayleigh published his mathematical description of how light scatters when it encounters particles much smaller than its wavelength. The intensity of scattered light, he demonstrated, varies inversely with the fourth power of the wavelength. This means blue light, with a wavelength around 450 nanometers, scatters approximately 16 times more efficiently than red light at 650 nanometers. The same physics that explains why Earth's daytime sky appears blue and sunsets glow red governs how artificial light spreads through the night atmosphere. Rayleigh could not have imagined his equations would one day describe a global transformation of human experience. Earth's lower atmosphere contains roughly 10 to the 19th power molecules per cubic centimeter, an almost incomprehensibly dense soup of nitrogen, oxygen, argon, carbon dioxide, water vapor, and trace gases. Each molecule measures less than a nanometer across, far smaller than visible light wavelengths. When a photon from a streetlight encounters one of these molecules, the oscillating electromagnetic field of the light wave induces the molecule's electrons to oscillate at the same frequency. These accelerating charges then radiate light in all directions, effectively redirecting a portion of the original beam. Multiply this interaction by the trillions upon trillions of molecules in the atmospheric column above any light source, and you create a three-dimensional diffuse glow that fills the entire sky dome. This is not reflection, as from a mirror or cloud. This is scattering, a fundamental reordering of light's directional flow into randomized omnidirectional radiation. The color temperature of the light source determines how efficiently this scattering occurs and how the resulting sky glow appears. Traditional high-pressure sodium vapor lamps, which dominated street lighting through the early teen, emit most of their light at 589 nanometers, a yellow-orange wavelength. This produces the characteristic amber glow of older city nights. Metal halide lamps emit a broader spectrum with significant blue and green components, creating whiter sky glow. Modern LED streetlights typically emit strong blue peaks between 440 and 460 nanometers, along with broader spectrum output, depending on the phosphor coating used. That blue component scatters far more aggressively than the yellow light of sodium lamps. A 4000 Kelvin LED streetlight, common in many cities, produces approximately 2.5 times more sky glow per lumen of ground illumination compared to the sodium lamps it replaces. The push toward energy efficiency through LEDs inadvertently created lights optimized for atmospheric scattering. But here's where it gets strange. The atmosphere does not scatter all this light uniformly in all directions. Rayleigh scattering produces a specific angular distribution pattern. Light scatters most strongly at 90 degrees to the incident beam and least in the forward and backward directions. This creates a ring-like distribution of scattered light around the original source when viewed from a distance. For someone standing directly beneath a streetlight, most of the scattered light goes sideways and upward, creating bright halos around the lamp and spreading illumination horizontally across the landscape. For someone 50 kilometers away, looking back toward a distant city, the scattered light appears as a dome of glow above the horizon, brighter near the source and fading with distance and altitude. This geometry means a single bright urban core impacts sky brightness across an enormous area, extending its influence far beyond the city limits. The scattering efficiency also depends on what else occupies the atmosphere. Water vapor increases scattering slightly, but aerosols, tiny solid or liquid particles suspended in air, amplify the effect dramatically. Urban aerosols from vehicle exhaust, industrial emissions, and other human activities typically measure between 0.1 and 10 micrometers in diameter, comparable to visible light wavelengths. These particles scatter light through a different process called Mie scattering, which is less wavelength dependent than Rayleigh scattering, but far more efficient at redirecting light. A humid, hazy night with high aerosol concentrations can produce 3 to 5 times more sky glow than a clear, dry night with identical ground lighting. This is why light pollution appears worst on muggy summer nights and improves temporarily after rainstorms clear particles from the air. The atmosphere itself becomes a variable amplifier of human light emissions. Think of the atmosphere as a vast diffusion screen, like the translucent material in a photography softbox, stretched across the entire sky. Every light source on the ground projects upward and outward into this screen, which then glows with the accumulated light from all sources within view. The screen's efficiency varies with wavelength, humidity, aerosol content, and altitude, but it always converts directional light into omnidirectional glow. From the ground, we see this glow superimposed on the cosmic background, the combined light from stars, galaxies, nebulae, and the faint airglow naturally produced by the upper atmosphere. When the artificial glow becomes brighter than the natural background, faint celestial objects vanish into the noise. The threshold is remarkably low. Sky glow just 1/10 the brightness of natural moonless night sky begins to obscure the faintest visible stars. At 1/3 natural brightness, the Milky Way becomes difficult to see. At equal brightness, it disappears entirely for most observers. Astronomers measure this brightness using magnitudes per square arc second, a system that seems deliberately designed to confuse the uninitiated. The scale is logarithmic and inverted, meaning smaller numbers represent brighter skies. Natural dark sky measures approximately 22 magnitudes per square arc-second in the visual band. Urban sky can measure 17 magnitudes per square arc-second or brighter, roughly 100 times more luminous than natural conditions. This factor of 100 in brightness translates to a reduction in visible star count from roughly 5,000 stars down to fewer than 500, and a complete loss of extended objects like the Milky Way, the Andromeda Galaxy, and most nebulae. The human eye cannot distinguish fine gradations at these light levels. You do not experience 100 times more brightness as overwhelming glare. You experience it as a slight brightening that makes stars vanish, as if someone slowly increased the ambient light in a room until candles became invisible. Scientists measure sky brightness using specialized instruments called sky quality meters, handheld devices containing a calibrated photodiode sensor covered by a wide-angle diffuser. Point the meter at the zenith, press a button, and it reports sky brightness in magnitudes per square arc-second. Professional observatories use more sophisticated systems, automated photometers mounted on telescopes that record sky brightness continuously across multiple wavelengths throughout the night. The Dark Sky Meter smartphone application achieves similar measurements by carefully calibrating the phone's camera sensor against known standards. Tens of thousands of these measurements, collected over years from locations worldwide, created the datasets underlying the 2016 World Atlas of Artificial Night Sky Brightness. The measurements reveal patterns invisible to casual observation. Sky brightness typically peaks a few hours after midnight, when human activity declines but lights remain on. It increases near the horizon, where you look through more atmosphere and accumulate light from more distant sources. It varies seasonally with tourist activity, holiday lighting, and agricultural schedules. The night sky breathes with human rhythms. Satellite measurements approach the problem from the opposite direction. The Suomi NPP satellite, launched in 2011, carries the Visible Infrared Imaging Radiometer Suite, or VIRS, which detects light in wavelengths from 500 to 900 nanometers, using a day-night band sensor sensitive enough to observe individual streetlights from orbit. Each night, VIRS creates a complete map of Earth's artificial lights at 750-meter resolution, capturing everything from megacities to fishing boats in the open ocean, to gas flares in remote oil fields. These images reveal the spatial distribution of light sources, but satellites cannot directly measure how bright the sky appears from the ground. The light the satellite detects is the fraction that escapes upward into space, typically 10 to 50% of total light output depending on fixture design. The light that scatters and creates sky glow is the fraction that spreads horizontally through the atmosphere, which satellites see only indirectly. Combining satellite data with atmospheric scattering models and ground-based measurements allows researchers to estimate sky brightness globally, filling in the gaps between direct observation points. The propagation of light pollution follows predictable mathematical patterns described by atmospheric radiative transfer equations, the same physics used to model how sunlight illuminates the daytime sky. Light intensity decreases with distance from the source, but not as rapidly as the inverse square law would suggest for propagation through empty space. Atmospheric scattering effectively redistributes light across large areas, creating a much gentler fall-off. A major city like Los Angeles affects sky brightness measurably at distances exceeding 300 kilometers. The megalopolis region of the eastern United States, stretching from Boston to Washington, creates a continuous zone of light pollution covering more than 150,000 square kilometers, where individual cities merge into a single luminous corridor. In Western Europe, light pollution from cities in Germany, France, Belgium, and the Netherlands creates interconnected domes of sky glow, covering much of the continent. From orbit at night, these regions glow as continuous fields of light, national borders invisible, the geography rewritten in photons. The temporal patterns reveal human behavior as precisely as any economic data. Light emissions rise sharply after sunset as streetlights activate and commercial lighting switches on. They peak in the early evening when both businesses and residences use maximum lighting. They decline slowly through the night as offices close, shops shut down, and households sleep, though they never approach zero in urban areas. Streetlights, parking lot illumination, and security lighting remain constant through the night, creating a baseline glow that never fades. Weekend nights show different patterns than weeknights. Holiday lighting creates dramatic seasonal peaks, particularly around Christmas and New Year, when decorative lighting can increase light emissions by 20 to 30% in residential areas. Even weather patterns appear in light data. Snowfall increases albedo, causing more light to reflect upward from the ground and increasing satellite measurements. These temporal signatures make light pollution a proxy measurement for human activity, economic vitality, and social organization. But conventional understanding fails to predict where light pollution will grow fastest. Development economics suggests that poorer nations should urbanize while maintaining dark rural areas, creating a pattern of bright cities surrounded by dark countryside. Instead, the most rapid growth in light pollution now occurs in developing nations experiencing economic expansion. As incomes rise, outdoor lighting becomes both affordable and desirable, a visible symbol of progress and security. Countries across Asia, Africa, and South America add artificial light faster than North America or Europe, regions where light pollution already saturates urban areas and grows mainly through sprawl. India's light emissions increased by more than 50% between 2012 and 2016. China's coastal provinces transformed from moderately lit to intensely bright in 2 decades. This pattern suggests light pollution will continue accelerating globally, even as wealthy nations implement modest controls. The darkest places on Earth are not poor rural areas in developing nations, but uninhabitable regions, deserts, ice sheets, open ocean, areas where humans cannot establish permanent presence. The evolution from early gas lighting to modern LED streetlights spans barely 2 centuries but represents a million-fold increase in artificial illumination intensity. In 1800, cities like London and Paris relied on gas lamps that produced roughly 15 lumens, about as bright as a modern birthday candle. Each lamp illuminated a tiny circle beneath it, leaving most streets in darkness. By 1900, electric arc lamps began appearing, producing thousands of lumens, but remaining rare and expensive. The brought widespread incandescent street lighting at hundreds of lumens per fixture. The introduced high-pressure sodium and mercury vapor lamps, approaching 10,000 lumens. Modern LED streetlights often exceed 15,000 lumens per fixture, and cities install them by the tens of thousands. This exponential growth in per-fixture output, combined with exponential growth in fixture count, created the transformation we see today. The night grew brighter in a compound acceleration that continues unabated. The human eye's adaptation mechanisms mask the change from immediate perception. Step from a bright room into darkness, and your eyes gradually adapt, becoming roughly 10,000 times more sensitive over 30 to 45 minutes as rhodopsin regenerates in rod cells and your pupils dilate. This process allowed humans to function in the naturally dark night for hundreds of thousands of years. But the process works in both directions. Live under perpetually bright skies, and your eyes never fully dark adapt. You lose the sensitivity needed to see faint stars, not because they have faded, but because your visual system has recalibrated to the altered environment. People who spend their entire lives in cities often report being genuinely shocked when they first see a truly dark sky, overwhelmed by the sheer number of stars visible, disoriented by the three-dimensional depth of the Milky Way structure. They are seeing what humans saw normally for all of history, but to them it appears alien and strange. The baseline has shifted, and a new generation accepts bright night skies as natural, while dark skies seem abnormal. This baseline shift became measurable in 1994 when the Northridge earthquake struck Los Angeles at 4:31 in the morning, cutting power across the city. In the sudden darkness, the Los Angeles emergency services received numerous calls from frightened residents reporting a strange, silvery cloud hovering over the city. They were seeing the Milky Way for the first time in their lives. Observatory staff later confirmed that the calls came in waves as different neighborhoods lost power, a direct correlation between blackout zones and reports of this mysterious phenomenon in the sky. An entire generation of urban dwellers had grown up without knowing what a natural night sky looked like. When they finally saw it, they perceived it as an anomaly, something wrong, possibly threatening. The universe had become unfamiliar to the people living beneath it. The history of artificial outdoor lighting begins not with electric lamps, but with fire. Ancient cities used torches soaked in pitch or oil to illuminate important thoroughfares and public spaces. Rome employed a corps of slaves called lanternari, who carried torches to light the paths of wealthy citizens walking at night. These flames provided local illumination measured in fractions of a lumen, barely enough to avoid obstacles and recognize faces at close range. The night remained fundamentally dark. In 1417, the mayor of London ordered residents to hang lanterns outside their homes during winter months, creating the first systematic street lighting, though the practice remained sporadic and dim. Paris introduced more consistent street lighting in 1667 under the direction of Nicolas de la Reynie, who installed approximately 2,700 candle lanterns throughout the city. By 1729, Paris had more than doubled this number to 5,000 lanterns, each containing multiple candles and lit from sunset to midnight. The first major transformation came with gas lighting in the early 19th century. William Murdoch demonstrated coal gas lighting at his home in Cornwall, England in 1792, and by 1807, London's Pall Mall became the first street illuminated by gas lamps. The technology spread rapidly. Baltimore installed gas streetlights in 1816, becoming the first American city with gas lighting. By 1823, over 40,000 gas lamps illuminated London streets, producing light equivalent to roughly 50 lumens per lamp, a 3- to 5-fold increase over oil lanterns. Gas lighting created the first widespread nighttime urban illumination, bright enough to enable reading and detailed work after dark. Charles Dickens described Victorian London's gas-lit streets as creating a permanent twilight, neither true day nor night, a new temporal zone unknown in human history. The comparison seems quaint now, but gaslighting represented humanity's first significant alteration of natural darkness at the scale of entire cities. Electric lighting emerged in the and immediately demonstrated its superiority. Arc lamps, which produce light by maintaining an electric arc between carbon electrodes, generated thousands of lumens from a single fixture. In 1878, Paris installed arc lamps along the Avenue de l'Opéra, and the brilliant white light drew enormous crowds who marveled at the artificial daylight. Cleveland, Ohio, became the first city to adopt arc lighting extensively in 1879, installing 12 lamps that each illuminated a radius of several city blocks. By 1880, New York's Madison Square featured an arc lamp tower 160 feet tall, topped with multiple arc lamps, visible for miles and casting stark shadows across the city. Contemporary accounts describe the experience as unsettling. The intense white light created harsh contrasts between brilliantly lit areas and deep shadows, eliminating the soft gradations of natural twilight. People complained of headaches and eye strain. Birds became confused and sang at night. Insects swarmed the lights in unprecedented numbers. The ecological and physiological impacts of artificial light pollution appeared immediately, though no one yet had the conceptual framework to understand them as connected phenomena. Incandescent bulbs, perfected by Thomas Edison and Joseph Swan in the UN, provided gentler light suitable for indoor use and smaller-scale outdoor applications. Edison's Pearl Street Station in New York, which began operation in 1882, served 85 customers with electric lighting, demonstrating the viability of centralized power distribution. By 1920, most major American and European cities had replaced gas lighting with electric streetlights using incandescent bulbs. These produced hundreds of lumens per fixture, bright enough to illuminate sidewalks and roadways, but still leaving most of the night sky visible. Photographs of New York City from the show illuminated streets creating islands of light, separated by extensive dark areas. Stars remained visible even in Manhattan. The post-World War II era brought revolutionary changes in lighting technology and urban development patterns. Mercury vapor lamps, introduced in the but widely adopted after 1945, produced 3 to 5 times more light per watt than incandescent bulbs. Their blue-white light became ubiquitous in parking lots, industrial areas, and highway lighting through the and. High-pressure sodium vapor lamps, developed in the and improved through the ik, offered even better efficiency along with a characteristic yellow-orange glow. By 1980, sodium vapor lamps dominated street lighting across North America and Europe, producing 10,000 to 20,000 lumens per fixture. Simultaneously, automobile-centric suburban development spread cities across vastly larger geographic areas. Los Angeles, which occupied roughly 100 square miles in 1920, sprawled across 500 square miles by 1970. Every square mile added thousands of street lights, parking lot lights, building illumination, and vehicle headlights. The total light output increased not linearly, but geometrically. The first systematic recognition of light pollution as a scientific problem emerged from the astronomy community in the RORs. In 1972, the Kitt Peak National Observatory in Arizona, established in 1958 in a remote desert location chosen specifically for its dark skies, published the first measurements showing measurable sky glow from Tucson, 60 miles away. By 1974, Tucson's light dome had brightened enough to interfere with sensitive observations. In 1976, Tucson implemented the first lighting ordinances specifically designed to reduce light pollution, requiring shields on outdoor fixtures to direct light downward rather than upward and sideways. The ordinances produced measurable improvements. Upward light emissions from Tucson decreased by roughly 30% between 1976 and 1980, demonstrating that light pollution could be controlled through policy without eliminating outdoor lighting entirely. Other observatories followed similar paths. Palomar Observatory, home to the 200-inch Hale telescope from 1948 until the Oahu, watched San Diego's light dome grow from a faint glow on the horizon in 1950 to a brilliant hemisphere dominating the southwestern sky by 1980. Mount Wilson Observatory above Los Angeles essentially ceased productive astronomical research in the as light from the Los Angeles basin made faint object observation impossible. In 1988, the International Dark Sky Association formed in Tucson with the mission of protecting night skies for astronomy, ecology, and human heritage. Early efforts focused on working with cities near major observatories, advocating for shielded lighting, limiting light intensity, and restricting certain wavelengths. Success remained limited. Light pollution continued to increase even around observatories with protective ordinances, driven by regional growth far beyond the control of local regulations. Satellite measurements revolutionized the study of light pollution by providing the first global view of artificial night lighting. The Defense Meteorological Satellite Program began capturing nighttime imagery using the Operational Line Scan system in 1972, initially for military intelligence purposes. These early images revealed cities as bright spots against dark backgrounds, but the sensors lacked the sensitivity and resolution to measure light pollution quantitatively. In 1996, the Operational Line Scan system received upgraded sensors that could detect much fainter light, enabling researchers to map global light emissions for the first time. Pierantonio Cinzano, Fabio Falci, and Christopher Elvidge used this data to create the first World Atlas of Artificial Night Sky Brightness, published in 2001. The atlas combined satellite data with atmospheric scattering models to estimate sky brightness at every location on Earth. The results shocked even experts who studied light pollution professionally. The 2001 atlas showed that approximately 2/3 of the global population lived under light-polluted skies, bright enough to impact astronomical observations. More than 40% of humanity never experienced true darkness. The Milky Way was invisible to roughly 20% of people worldwide. In the United States and European Union, the numbers were far worse. 99% of the population lived under light-polluted skies. 62% could not see the Milky Way. The data revealed light pollution not as a local problem around observatories, but as a global transformation of the night environment affecting billions of people. The transition to LED lighting, which accelerated dramatically after 2010, created both opportunities and setbacks for dark sky preservation. LEDs offer extraordinary energy efficiency, converting roughly 40 to 50% of electrical energy into visible light, compared to just 5% for incandescent bulbs and 15% for sodium vapor lamps. This efficiency could, in theory, allow cities to maintain adequate illumination while using less total energy and producing less total light output. The first cities to replace streetlights with LEDs in the early chose high color temperature LEDs, typically 4,000 to 5,000 Kelvin, which produce bright white light with strong blue wavelength components. These blue wavelengths scatter extremely efficiently in the atmosphere and suppress melatonin production in humans and animals far more effectively than the yellow light of sodium lamps. Los Angeles completed one of the world's largest LED streetlight conversions between 2013 and 2015, replacing 140,000 high-pressure sodium lamps with LEDs. The city reported energy savings of 63% and cost savings of $9 million annually. However, satellite measurements showed that while upward light emissions decreased by approximately 10%, the shift to blue-rich white light created significant new problems. The American Medical Association issued a position statement in 2016, warning that LED streetlights with color temperatures above 3,000 Kelvin posed health and safety risks due to blue wavelength light exposure. The statement recommended limiting LED color temperature to 3,000 Kelvin or lower, ideally matching the yellow-orange spectrum of the sodium lamps being replaced. Some cities responded by selecting warmer LEDs for new installations. Others, having already committed to contracts for high-color temperature LEDs, proceeded with installations that increased certain types of light pollution, even while reducing energy consumption. Ecological research revealed impacts that earlier generations could not have anticipated. In 2000, researchers discovered that artificial light disrupts magnetic compass orientation in migratory birds. Studies published in 2014 showed that light pollution interferes with dung beetle navigation, which relies on polarized moonlight and the Milky Way to orient while rolling dung balls. Research from 2016 demonstrated that bat species shift their foraging behavior in response to streetlight spectrum, with some species attracted to insects aggregating around lights while other species avoid lit areas entirely. A comprehensive review published in 2017 documented impacts on organisms ranging from sea turtles to zooplankton, from plants to corals, affecting reproduction, navigation, foraging, predator-prey interactions, and seasonal timing. The night environment, it became clear, supports complex ecosystems that evolved under consistent darkness for hundreds of millions of years. Flooding that environment with light disrupts ecological processes at fundamental levels. The scientific understanding of light pollution's health impact similarly evolved from preliminary observations to rigorous epidemiological evidence. Early studies in the found correlations between night shift work and increased cancer rates, but could not isolate the specific causal mechanisms. Research in the established that light exposure at night suppresses melatonin production in dose-dependent ways, with blue wavelengths having the strongest effect. By 2010, laboratory studies confirmed that chronic circadian disruption from light at night promoted tumor growth in animal models. Large-scale epidemiological studies published between 2015 and 2020 linked outdoor light exposure at night with increased risks of breast cancer, prostate cancer, obesity, and mood disorders in human populations. The mechanisms involve melatonin suppression, circadian rhythm disruption, sleep fragmentation, and altered hormonal signaling. The evidence remains correlational rather than definitively causal, but the consistency across multiple studies and biological plausibility of the mechanisms have convinced most researchers that artificial light at night poses genuine health risks at population scales. The pattern that emerges from this history is one of accelerating transformation with delayed recognition of consequences. Each new lighting technology arrived promising progress, efficiency, safety, and prosperity. Gas lighting made cities safer and enabled new forms of commerce and social life. Electric lighting increased productivity and quality of life. LED lighting reduces energy consumption and operational costs. These benefits are real and tangible, but each technological advance also eliminated more darkness, brightened the night sky further, extended human activity deeper into the circadian night, and disrupted natural systems in ways that took decades to recognize and measure. We are now 7 generations into this transformation, having compressed the shift from firelight to LED illumination into barely 2 centuries, and only recently began understanding the full scope of what we have altered. Architected historical light pollution narrative with dates and technological evolution. This baseline shift became measurable in 1994, when the Northridge earthquake struck Los Angeles at 4:31 in the morning, cutting power across the city. In the sudden darkness, the Los Angeles Emergency Services received numerous calls from frightened residents reporting a strange, silvery cloud hovering over the city. They were seeing the Milky Way for the first time in their lives. Observatory staff later confirmed that the calls came in waves as different neighborhoods lost power, a direct correlation between blackout zones and reports of this mysterious phenomenon in the sky. An entire generation of urban dwellers had grown up without knowing what a natural night sky looked like. When they finally saw it, they perceived it as an anomaly, something wrong, possibly threatening. The universe had become unfamiliar to the people living beneath it. The history of artificial outdoor lighting begins not with electric lamps, but with fire. Ancient cities used torches soaked in pitch or oil to illuminate important thoroughfares and public spaces. Rome employed a corps of slaves called lanternari, who carried torches to light the paths of wealthy citizens walking at night. These flames provided local illumination measured in fractions of a lumen, barely enough to avoid obstacles and recognize faces at close range. The night remained fundamentally dark. In 1417, the mayor of London ordered residents to hang lanterns outside their homes during winter months, creating the first systematic street lighting, though the practice remained sporadic and dim. Paris introduced more consistent street lighting in 1667 under the direction of Nicolas de la Reynie, who installed approximately 2,700 candle lanterns throughout the city. By 1729, Paris had more than doubled this number to 5,572 lanterns, each containing multiple candles and lit from sunset to midnight. The first major transformation came with gas lighting in the early 19th century. William Murdoch demonstrated coal gas lighting at his home in Cornwall, England in 1792, and by 1807, London's Pall Mall became the first street illuminated by gas lamps. The technology spread rapidly. Baltimore installed gas streetlights in 1816, becoming the first American city with gas lighting. By 1823, over 40,000 gas lamps illuminated London streets, producing light equivalent to roughly 50 lumens per lamp, a 3- to 5-fold increase over oil lanterns. Gas lighting created the first widespread nighttime urban illumination bright enough to enable reading and detailed work after dark. Charles Dickens described Victorian London's gaslit streets as creating a permanent twilight, neither true day nor night, a new temporal zone unknown in human history. The comparison seems quaint now, but gaslighting represented humanity's first significant alteration of natural darkness at the scale of entire cities. Electric lighting emerged in the EU and immediately demonstrated its superiority. Arc lamps, which produce light by maintaining an electric arc between carbon electrodes, generated thousands of lumens from a single fixture. In 1878, Paris installed arc lamps along the Avenue de l'Opéra, and the brilliant white light drew enormous crowds who marveled at the artificial daylight. Cleveland, Ohio, became the first city to adopt arc lighting extensively in 1879, installing 12 lamps that each illuminated a radius of several city blocks. By 1880, New York's Madison Square featured an arc lamp tower, 160 feet tall, topped with multiple arc lamps visible for miles and casting stark shadows across the city. Contemporary accounts describe the experience as unsettling. The intense white light created harsh contrasts between brilliantly lit areas and deep shadows, eliminating the soft gradations of natural twilight. People complained of headaches and eye strain. Birds became confused and sang at night. Insects swarmed the lights in unprecedented numbers. The ecological and physiological impacts of artificial light pollution appeared immediately, though no one yet had the conceptual framework to understand them as connected phenomena. Incandescent bulbs, perfected by Thomas Edison and Joseph Swan in the D's, provided gentler light suitable for indoor use and smaller-scale outdoor applications. Edison's Pearl Street Station in New York, which began operation in 1882, served 85 customers with electric lighting, demonstrating the viability of centralized power distribution. By 1920, most major American and European cities had replaced gas lighting with electric streetlights using incandescent bulbs. These produced hundreds of lumens per fixture, bright enough to illuminate sidewalks and roadways, but still leaving most of the night sky visible. Photographs of New York City from the show illuminated streets creating islands of light, separated by extensive dark areas. Stars remained visible even in Manhattan. The post-World War II era brought revolutionary changes in lighting technology and urban development patterns. Mercury vapor lamps, introduced in the but widely adopted after 1945, produced 3 to 5 times more light per watt than incandescent bulbs. Their blue-white light became ubiquitous in parking lots, industrial areas, and highway lighting through the high-pressure sodium vapor lamps, developed in the and improved through the IG, offered even better efficiency along with a characteristic yellow-orange glow. By 1980, sodium vapor lamps dominated street lighting across North America and Europe, producing 10,000 to 20,000 lumens per fixture. Simultaneously, automobile-centric suburban development spread cities across vastly larger geographic areas. Los Angeles, which occupied roughly 100 square miles in 1920, sprawled across 500 square miles by 1970. Every square mile added thousands of streetlights, parking lot lights, building illumination, and vehicle headlights. The total light output increased not linearly, but geometrically. The first systematic recognition of light pollution as a scientific problem emerged from the astronomy community in the GIWI. In 1972, the Kitt Peak National Observatory in Arizona, established in 1958 in a remote desert location chosen specifically for its dark skies, published the first measurements showing measurable sky glow from Tucson, 60 miles away. By 1974, Tucson's light dome had brightened enough to interfere with sensitive observations. In 1976, Tucson implemented the first lighting ordinances specifically designed to reduce light pollution, requiring shields on outdoor fixtures to direct light downward rather than upward and sideways. The ordinances produced measurable improvements. Upward light emissions from Tucson decreased by roughly 30% between 1976 and 1980, demonstrating that light pollution could be controlled through policy without eliminating outdoor lighting entirely. Other observatories followed similar paths. Palomar Observatory, home to the 200-inch Hale telescope from 1948 until the DGN, watched San Diego's light dome grow from a faint glow on the horizon in 1950 to a brilliant hemisphere dominating the southwestern sky by 1980. Mount Wilson Observatory above Los Angeles essentially ceased productive astronomical research in the as light from the Los Angeles basin made faint object observation impossible. In 1988, the International Dark Sky Association formed in Tucson with the mission of protecting night skies for astronomy, ecology, and human heritage. Early efforts focused on working with cities near major observatories, advocating for shielded lighting, limiting light intensity, and restricting certain wavelengths. Success remained limited. Light pollution continued to increase even around observatories with protective ordinances, driven by regional growth far beyond the control of local regulations. Satellite measurements revolutionized the study of light pollution by providing the first global view of artificial night lighting. The Defense Meteorological Satellite Program began capturing nighttime imagery using the Operational Line Scan system in 1972, initially for military intelligence purposes. These early images revealed cities as bright spots against dark backgrounds, but the sensors lacked the sensitivity and resolution to measure light pollution quantitatively. In 1996, the Operational Line Scan system received upgraded sensors that could detect much fainter light, enabling researchers to map global light emissions for the first time. Pierantonio Cinzano, Fabio Falci, and Christopher Elvidge used this data to create the first World Atlas of Artificial Night Sky Brightness, published in 2001. The atlas combined satellite data with atmospheric scattering models to estimate sky brightness at every location on Earth. The results shocked even experts who studied light pollution professionally. The 2001 atlas showed that approximately 2/3 of the global population lived under light-polluted skies, bright enough to impact astronomical observations. More than 40% of humanity never experienced true darkness. The Milky Way was invisible to roughly 20% of people worldwide. In the United States and European Union, the numbers were far worse. 99% of the population lived under light-polluted skies. 62% could not see the Milky Way. The data revealed light pollution not as a local problem around observatories, but as a global transformation of the night environment, affecting billions of people. The transition to LED lighting, which accelerated dramatically after 2010, created both opportunities and setbacks for dark sky preservation. LEDs offer extraordinary energy efficiency, converting roughly 40 to 50% of electrical energy into visible light, compared to just 5% for incandescent bulbs and 15% for sodium vapor lamps. This efficiency could, in theory, allow cities to maintain adequate illumination while using less total energy and producing less total light output. The first cities to replace streetlights with LEDs in the early chose high-color temperature LEDs, typically 4,000 to 5,000 Kelvin, which produce bright white light with strong blue wavelength components. These blue wavelengths scatter extremely efficiently in the atmosphere and suppress melatonin production in humans and animals far more effectively than the yellow light of sodium lamps. Los Angeles completed one of the world's largest LED streetlight conversions between 2013 and 2015, replacing 140,000 high-pressure sodium lamps with LEDs. The city reported energy savings of 63% and cost savings of $9 million annually. However, satellite measurements showed that while upward light emissions decreased by approximately 10%, the shift to blue-rich white light created significant new problems. The American Medical Association issued a position statement in 2016, warning that LED streetlights with color temperatures above 3,000 Kelvin posed health and safety risks due to blue wavelength light exposure. The statement recommended limiting LED color temperature to 3,000 Kelvin or lower, ideally matching the yellow-orange spectrum of the sodium lamps being replaced. Some cities responded by selecting warmer LEDs for new installations. Others, having already committed to contracts for high-color temperature LEDs, proceeded with installations that increased certain types of light pollution, even while reducing energy consumption. Ecological research revealed impacts that earlier generations could not have anticipated. In 2000, researchers discovered that artificial light disrupts magnetic compass orientation in migratory birds. Studies published in 2014 showed that light pollution interferes with dung beetle navigation, which relies on polarized moonlight and the Milky Way to orient while rolling dung balls. Research from 2016 demonstrated that bat species shift their foraging behavior in response to streetlight spectrum, with some species attracted to insects aggregating around lights while other species avoid lit areas entirely. A comprehensive review published in 2017 documented impacts on organisms ranging from sea turtles to zooplankton, from plants to corals, affecting reproduction, navigation, foraging, predator-prey interactions, and seasonal timing. The night environment, it became clear, supports complex ecosystems that evolved under consistent darkness for hundreds of millions of years. Flooding that environment with light disrupts ecological processes at fundamental levels. The scientific understanding of light pollution's health impacts similarly evolved from preliminary observations to rigorous epidemiological evidence. Early studies found correlations between night shift work and increased cancer rates, but could not isolate the specific causal mechanisms. Research established that light exposure at night suppresses melatonin production in dose-dependent ways, with blue wavelengths having the strongest effect. By 2010, laboratory studies confirmed that chronic circadian disruption from light at night promoted tumor growth in animal models. Large-scale epidemiological studies published between 2015 and 2020 linked outdoor light exposure at night with increased risks of breast cancer, prostate cancer, obesity, and mood disorders in human populations. The mechanisms involve melatonin suppression, circadian rhythm disruption, sleep fragmentation, and altered hormonal signaling. The evidence remains correlational rather than definitively causal, but the consistency across multiple studies and biological plausibility of the mechanisms have convinced most researchers that artificial light at night poses genuine health risks at population scales. The pattern that emerges from this history is one of accelerating transformation with delayed recognition of consequences. Each new lighting technology arrived promising progress, efficiency, safety, and prosperity. Gas lighting made cities safer and enabled new forms of commerce and social life. Electric lighting increased productivity and quality of life. LED lighting reduces energy consumption and operational costs. These benefits are real and tangible. But each technological advance also eliminated more darkness, brightened the night sky further, extended human activity deeper into the circadian night, and disrupted natural systems in ways that took decades to recognize and measure. We are now 7 generations into this transformation, having compressed the shift from firelight to LED illumination into barely 2 centuries, and only recently began understanding the full scope of what we have altered. The transformation of Earth's night sky exists within a broader context that makes it simultaneously insignificant and extraordinary. From a cosmic perspective, the light we emit barely registers. Earth's total artificial light output amounts to roughly 500 terawatts of visible light energy, which sounds enormous until you compare it to the Sun's output, reaching Earth of 170,000 terawatts. Our artificial lights are 1/3000th as bright as sunlight, a rounding error in the energy budget of the Earth-Sun system. An alien astronomer observing Earth from even the nearest star, Proxima Centauri at just over 4 light-years away, would struggle to detect our artificial lights against the reflected sunlight from Earth's clouds and oceans. Our light pollution is a local phenomenon, confined to the thin shell of atmosphere immediately surrounding our planet. We have not dimmed the stars, we have only dimmed our view of them. Yet from a biological and cultural perspective, this local transformation carries profound significance. Earth orbits an unremarkable yellow dwarf star in the outer regions of a spiral galaxy containing hundreds of billions of similar stars. Our solar system resides roughly 26,000 light-years from the galactic center, embedded in the Orion Arm, a minor spiral arm connecting 2 major arms. From this location, the Milky Way appears as a luminous band spanning the entire sky because we view our galaxy edge-on from within. We see the combined light of hundreds of billions of stars, mostly too faint to resolve individually, blending into a continuous glow. This view is specific to our position. An observer in the galactic halo far above or below the disk would see the Milky Way as a spiral structure viewed face-on, beautiful but fundamentally different. An observer in a globular cluster orbiting the galactic edge would see individual nearby stars, but no band of continuous light. Our experience of the Milky Way depends entirely on where we happen to be located in the galaxy. The same principle applies to our moment in time. For roughly 4 billion years after Earth formed, the planet had no observers capable of contemplating the night sky. Single-celled organisms, early multicellular life, the first animals, none possessed the neural architecture to perceive and wonder about the stars. The earliest hominids perhaps noticed the sky, but left no record of their thoughts. Only in the last few 100,000 years did anatomically modern humans emerge with brains capable of asking cosmological questions. For nearly all of that time, every human who ever lived saw essentially the same night sky, the same Milky Way, the same patterns of stars. Then, in the most recent 1/10,000th of human history, roughly the last century, we transformed that view so dramatically that most people alive today will never see what every one of their ancestors saw. We live at a unique inflection point, the brief transition period between universal access to dark skies and the possible permanent loss of that experience for most of humanity. This creates a paradox of visibility and knowledge. We know more about the universe now than at any point in human history. We understand that the Milky Way is a barred spiral galaxy containing 200 billion to 400 billion stars. We know it spans 100,000 light-years in diameter and orbits a supermassive black hole at its center with a mass of approximately 4 million suns. We have measured its rotation curve, mapped its spiral structure, catalogued its stellar populations, and traced its collision history with other galaxies. We possess this knowledge despite seeing less of the Milky Way directly than our ancestors did. Professional astronomers using the world's most powerful telescopes, deliberately located in the darkest remaining places on Earth and increasingly in space beyond Earth's atmosphere, gather the data that reveals galactic structure. Meanwhile, the general population lives under skies where the Milky Way has vanished. Knowledge and experience have divorced from one another. We understand the cosmos intellectually while losing direct sensory connection to it. The measurement challenges in quantifying light pollution reveal similar tensions between precision and comprehension. Sky brightness measurements achieved through handheld meters or smartphone applications provide precise numbers, magnitudes per square arc second, calculated to hundredths of a magnitude. But these numbers fail to capture subjective experience. A sky measuring 19.5 magnitudes per square arc second shows hundreds of stars and a visible Milky Way to a trained observer with dark, adapted eyes. An inexperienced observer at the same location might see far fewer stars, their vision not yet adapted, their pattern recognition not yet trained. Two people at the same location under identical physical conditions report significantly different experiences of the night sky based on their personal history, expectations, and perceptual skills. The physics is objective, but the loss is partially subjective, impossible to quantify fully. Satellite measurements provide comprehensive geographic coverage but introduce different ambiguities. The Suomi NPP satellite's ITAR's day-night band detects light at wavelengths from 500 to 900 nanometers, covering green through near-infrared. This captures most artificial light sources effectively, but misses short wavelength blue and violet light below 500 nanometers, precisely the wavelengths that scatter most efficiently and create the worst sky glow. LED streetlights with strong blue components at 440 to 460 nanometers are partially invisible to viewers, causing satellite measurements to underestimate the true sky brightness impact of LED lighting. Conversely, VIIRS detects near-infrared wavelengths that human eyes cannot see, potentially overestimating the visual impact of certain light sources. Converting satellite measurements to predicted sky brightness requires atmospheric models that account for scattering efficiency, aerosol content, humidity, and ground albedo, each introducing additional uncertainty. The temporal variability of light pollution creates measurement challenges that complicate long-term trend analysis. A city's light emissions vary hour by hour, day by day, season by season. Sporting events, concerts, holidays, and seasonal tourism create temporary surges in lighting. Power outages, economic recessions, and pandemic lockdowns cause temporary decreases. Satellite measurements provide only snapshots, typically 1 or 2 passes per location per night, missing the temporal variation. Ground-based continuous monitoring captures this variation, but only at specific locations. Synthesizing these different data sources into coherent global trends requires sophisticated statistical methods and assumptions about how sampled locations represent larger regions. The uncertainty in global estimates of light pollution growth rates may be as high as 20 to 30%, enough to obscure whether interventions are working or whether the problem continues accelerating unchecked. Our position as both victims and perpetrators of light pollution creates ethical complexities absent from most environmental problems. Climate change affects everyone, but results primarily from the actions of wealthy nations and individuals with high carbon footprints. Biodiversity loss impacts ecosystems globally, but stems from specific activities like deforestation and overfishing in particular regions. Light pollution affects everyone with eyes but results from individual choices by billions of people installing porch lights, businesses illuminating storefronts, municipalities operating streetlights. The person who cannot see the stars is typically the same person whose lights contribute to the problem. There is no clear victim-perpetrator divide, no simple assignment of responsibility or obligation. Everyone bears some responsibility. Everyone suffers some loss. This diffusion of causality makes collective action extraordinarily difficult. The geographic distribution of light pollution correlates almost perfectly with wealth and development. North America, Europe, Japan, South Korea, the Persian Gulf states, Australia, urban coastal China, all the world's economically developed regions shine brightly at night. Sub-Saharan Africa, rural South Asia, the Amazon basin, Central Australia, northern Canada, Siberia. These regions remain dark, not because their inhabitants value darkness, but because they lack the infrastructure and wealth to illuminate extensively. As nations develop economically, one of the first visible changes from space is increasing nighttime illumination. Light pollution functions as a proxy measure for industrialization, urbanization, and rising living standards. The darkest places on Earth are either uninhabitable or impoverished. The brightest places are prosperous and developed. This correlation makes light pollution difficult to criticize without appearing to oppose development itself. Yet location matters for reasons beyond economics. The experience of light pollution varies dramatically with geography even within wealthy nations. Someone living in rural Montana experiences Class 2 or Class 3 skies, with minimal light pollution, the Milky Way clearly visible, thousands of stars apparent to the naked eye. Someone living 50 miles from New York City experiences Class 7 or Class 8 skies, the Milky Way invisible, fewer than 300 stars visible. Both live in the United States. Both pay similar amounts in taxes that fund public lighting. Both benefit from modern infrastructure. But their experience of the night sky differs as dramatically as if they lived on different planets. This geographic inequality in access to dark skies exists within every developed nation, typically following urban-rural gradients, though sprawl and commuter traffic progressively eliminate dark sky areas even far from city centers. The concept of dark sky preserves attempts to address this geographic inequality by protecting specific areas from light pollution through regulation and planning. The International Dark Sky Association has certified more than 130 dark sky places worldwide as of 2020, including national parks, reserves, communities, and sanctuaries. Natural Bridges National Monument in Utah became the first certified international dark sky park in 2007. Big Bend National Park in Texas, Death Valley National Park in California, Cherry Springs State Park in Pennsylvania, and numerous other locations have received certification based on measured sky quality, protection policies, and public outreach efforts. These preserves serve multiple functions, protecting astronomical observations, preserving habitat for nocturnal species, and providing the general public with access to natural darkness increasingly rare elsewhere. But dark sky preserves reveal a troubling limitation. They work by defining darkness as something that exists in designated zones, rather than as the natural baseline condition. This represents a fundamental inversion of historical norms. For all of human history until very recently, darkness was default and light was exception. Now light is default and darkness is exceptional, something that must be actively protected in special reserves like endangered species. The existence of dark sky parks, while valuable, tacitly accepts that most of the planet will remain light polluted. They function as museums preserving an experience that was once universal, accessible now only to those who can travel to specific remote locations. This is better than losing dark skies entirely, but it is not restoration. It is managed preservation of remnants. The relationship between light pollution and other forms of environmental degradation creates feedback loops that amplify impacts. Air pollution increases atmospheric scattering, making light pollution worse. Light pollution disrupts insect populations, which affects pollination and ecosystem health, which impacts agriculture and biodiversity. Energy generation for artificial lighting produces carbon emissions, contributing to climate change, which alters cloud cover patterns that affect both light scattering and astronomical observations. Sprawling urban development that increases light pollution also fragments habitats, increases vehicle emissions, and transforms landscapes. These problems interconnect in ways that make them difficult to address individually. Solving light pollution requires addressing energy policy, urban planning, economic development patterns, and cultural attitudes about light and darkness. Our moment in history offers a strange dual perspective. We live late enough to have created light pollution at scales that affect billions of people, but early enough that some individuals alive today remember when the Milky Way was visible from cities. Someone born in 1940 in what would become suburban Los Angeles saw the Milky Way as a child and watched it vanish over their lifetime. They experienced both worlds, before and after. In another generation, this transitional perspective will be gone. Everyone alive will have been born into light-polluted conditions, and the memory of universal dark skies will exist only in historical records and preserved photographs. We are the last generation with living connection to the astronomical heritage every human shared for hundreds of thousands of years. What we choose to do with this knowledge and experience will determine whether future generations even know what they are missing. The measurement paradox emerged clearly only after 2012, when satellite data began showing something that contradicted ground observations in systematic ways. Sideways, cities converting to LED streetlights reported dramatic reductions in energy consumption, often 50 to 70% decreases. Satellite measurements from the CIR's day-night band confirmed significant reductions in upward light emissions, typically 10 to 20% decreases in radiance measured from orbit. Policymakers celebrated these results as evidence that LED technology was solving light pollution while reducing energy costs. But ground-based sky brightness measurements told a different story. In many locations where satellites detected decreasing light emissions, observers with calibrated sky quality meters recorded increasing sky brightness, particularly at blue wavelengths. The two primary methods for assessing light pollution produced opposite conclusions about whether the problem was improving or worsening. Method 1 relies on satellite radiometry combined with atmospheric scattering models. The Suomi NPP satellite orbits Earth at an altitude of approximately 830 kilometers, passing over each location once per night around 1:30 a.m. local time. The VIOS day-night band sensor measures upward radiance in wavelengths from 500 to 900 nanometers, with radiometric calibration traceable to laboratory standards. Researchers take this radiance data, which represents light escaping upward into space, and feed it into radiative transfer models that simulate how light propagates through the atmosphere. These models account for molecular Rayleigh scattering, aerosol Mie scattering, ground albedo, atmospheric temperature and pressure profiles, and the spectral characteristics of different light sources. The model's output predicted sky brightness at ground level across the entire electromagnetic spectrum detectable from satellites. This approach provides global coverage, consistent methodology, and the ability to estimate sky brightness even in locations without ground-based observers. Satellite-based predictions for cities converting from high-pressure sodium to LED streetlights typically show modest improvements in sky brightness, usually 5 to 15% reductions in overall luminance. The models predict these improvements based on reduced total light output and better fixture shielding, as many LED conversions include upgrades to fully shielded fixtures that direct zero light above the horizontal plane. For a city like Los Angeles, which reduced upward light emissions by approximately 10% through LED conversion, atmospheric scattering models predicted corresponding reductions in zenith sky brightness of roughly 8 to 12%. Similar predictions emerged for cities across North America and Europe, implementing LED conversions between 2010 and 2020. The satellite data suggested LED technology was delivering on its promise to reduce light pollution while maintaining adequate illumination. Method 2 uses ground-based photometry, direct measurements of sky brightness taken from the surface using calibrated instruments. Sky quality meters, handheld devices containing photodiode sensors with specific spectral response curves, measure sky brightness in magnitudes per square arc second. Professional astronomical photometers provide higher precision and broader spectral coverage, measuring brightness in multiple wavelength bands from ultraviolet through near-infrared. These instruments detect all light reaching the observer from the sky dome, including scattered artificial light, natural air glow, zodiacal light, starlight, and galactic light. Observers typically measure at the zenith to minimize atmospheric path length and avoid horizon brightening. Thousands of measurements collected over years from the same locations create time series showing how sky brightness changes as ground lighting evolves. Ground-based measurements in cities converting to LED streetlights frequently show sky brightness increases, particularly in blue wavelengths between 400 and 500 nanometers. A comprehensive study published in 2017 by Christopher Kaiber and colleagues analyzed global VIR satellite data from 2012 to 2016 and found that artificially lit outdoor areas grew by more than 2% per year. Globally, while already lit areas increased in brightness by more than 2% annually. The study compared these satellite measurements with subjective reports from citizen scientists participating in the Globe at Night program, where observers estimate naked eye limiting magnitude by comparing the visible sky to reference star charts. The citizen science data showed worsening light pollution in most locations, consistent with ground-based measurements, but contradicting the expectation that LED adoption would reduce light pollution. The disagreement reached 20 to 40% in some cities, meaning ground observers reported sky brightness 20 to 40% higher than satellite models predicted. This discrepancy should not exist if both methods measure the same phenomenon accurately. Satellite radiance measurements and ground-based sky brightness observations are different perspectives on the same physical process, light scattering in Earth's atmosphere. Conservation of energy requires that light either escapes to space, gets absorbed in the atmosphere, or reaches the ground. Satellites measure the escaping fraction. Ground instruments measure the fraction reaching observers. Atmospheric absorption accounts for the difference. If satellites detect less upward light, ground-based measurements should show corresponding decreases in sky brightness, assuming constant atmospheric conditions and accounting for spectral differences in measurement sensitivity. The fact that these measurements diverged systematically after LED adoption indicates that something fundamental changed in ways the models failed to predict. The explanation lies in spectral distribution and measurement sensitivity. High-pressure sodium lamps emit narrow-band yellow-orange light centered at 589 nanometers. FIORS detects this wavelength efficiently as it falls near the peak sensitivity of the day-night band sensor. Sky quality meters also detect 589 nanometer light well, though their spectral response differs slightly from VIORS. When cities replace sodium lamps with LEDs, they typically choose lights with color temperatures between 3000 and 5000 Kelvin, which emit broadband spectra containing significant energy at blue wavelengths below 500 nanometers. VIOR's day-night band sensitivity drops sharply below 500 nanometers, essentially blind to wavelengths shorter than 480 nanometers. This means satellites underdetect blue light emissions compared to yellow light emissions for the same photometric intensity. Meanwhile, the atmosphere scatters blue light far more efficiently than yellow light. Rayleigh scattering intensity varies with the inverse fourth power of wavelength. Light at 450 nanometers scatters approximately 2.5 times more efficiently than light at 589 nanometers. This means even if total light output decreases, shifting the spectrum toward blue wavelengths can increase total scattered light in the atmosphere. An LED streetlight producing 20% less total lumens than the sodium lamp it replaces, but with 40% of its output in blue wavelengths rather than 10%, can create more sky glow despite lower total output. The satellite sees reduced radiance because it underweights blue light. The ground observer sees increased sky brightness because the atmosphere scatters blue light so effectively. Human photopic vision, the cone-based color vision system that operates under bright light conditions, shows peak sensitivity at 555 nanometers in the yellow-green range. Scotopic vision, the rod-based system that dominates under low light conditions, peaks at 507 nanometers in the blue-green range. At night, when rod cells dominate human vision, we are more sensitive to blue wavelengths than standard photometric measurements indicate. Blue-rich LED light appears brighter to dark-adapted human eyes than radiometric measurements suggest. This means the subjective experience of LED light pollution may exceed what physical instruments calibrated to photopic vision would predict. The human eye essentially acts as a blue-sensitive detector under dark conditions, registering increased sky brightness even when total radiometric measurements might show decreases. The magnitude of this effect becomes clear in detailed spectral measurements. Studies comparing high-pressure sodium and LED streetlights with identical ground-level illuminance found that LEDs at 4000 Kelvin color temperature produced 40 to 60% more short-wavelength blue light than sodium lamps. Atmospheric scattering models incorporating these spectral differences predicted that zenith sky brightness in the blue band would increase by 25 to 35% for LED conversions, even while total upward radiance decreased by 10%. Ground-based spectral photometry confirmed these predictions. Cities like Madrid, Vienna, and Tucson, which carefully measured sky brightness before and after LED conversions using calibrated photometers, observed blue band sky brightness increases of 20 to 40%, despite reductions in total upward light flux and energy consumption. This creates severe implications for cosmological observations and biological systems. Astronomical photometry uses standardized filter bands that isolate specific wavelength ranges. The B band, covering blue wavelengths from roughly 380 to 480 nanometers, is essential for measuring stellar temperatures, chemical compositions, and distances. Increased blue band sky brightness directly degrades B band astronomical observations, reducing the faintness limit for detectable objects and increasing photometric uncertainty. Observatories that spent decades developing techniques to cope with yellow sodium light pollution found their methods inadequate for blue LED light pollution, which penetrates different atmospheric windows and affects different scientific programs. The Hubble Space Telescope, operating above Earth's atmosphere, remains unaffected, but ground-based telescopes comprising the majority of astronomical infrastructure face new challenges. Biological impacts similarly concentrate in blue wavelengths. Circadian photoreception in mammals, including humans, depends on intrinsically photosensitive retinal ganglion cells containing melanopsin, a photopigment with peak sensitivity near 480 nanometers in the blue range. Blue light exposure at night suppresses melatonin production far more effectively than yellow or red light. A study published in 2019 found that 4,000 Kelvin LED light suppressed melatonin by approximately 50%, more than 2,700 Kelvin warm LED light, for the same photopic illuminance. This means LED streetlights at common color temperatures produce circadian disruption disproportionate to their illuminance, creating health impacts not captured by traditional lighting metrics. The American Medical Association's 2016 recommendation to limit LED color temperature to 3,000 Kelvin responded directly to this evidence. The stakes extend beyond immediate health and astronomical concerns to fundamental questions about how we measure and regulate environmental quality. Light pollution ordinances typically specify maximum illuminance in lux, or foot candles, metrics based on photopic human vision. These regulations made sense when all streetlights used similar spectral distributions. But with LED lighting offering arbitrary spectral control, two fixtures producing identical photopic illuminance can create vastly different sky glow, circadian disruption, and astronomical interference depending on their spectral output. Current regulations fail to capture these distinctions. A city could comply fully with light pollution ordinances while dramatically increasing blue light emissions and worsening both sky brightness and biological impacts. The regulatory framework developed over decades for traditional lighting became obsolete nearly overnight with LED adoption. This regulatory gap creates perverse incentives. LED manufacturers market high-color temperature lights as providing better visibility and security, claims supported by photopic vision metrics showing improved color rendering. Cities adopt these lights in good faith, seeking to improve public safety while reducing energy costs. The installations comply with existing ordinances. Energy consumption decreases as promised. But sky brightness increases in ways current regulations do not capture. Astronomical observations degrade, circadian disruption worsens, and nocturnal ecosystems face new pressures. Everyone follows the rules. The problem gets worse. This pattern reveals how technological change can outpace regulatory adaptation, creating situations where optimal individual choices produce harmful collective outcomes. The scientific community's response has been to develop new metrics that account for spectral effects. The melanopic lux, a measurement weighted by melanopsin's spectral sensitivity rather than photopic vision, captures circadian impact more accurately than standard illuminance. The scotopic to photopic ratio quantifies how bright a light source appears to dark-adapted vision relative to light-adapted vision, useful for assessing how humans actually perceive nighttime lighting. Spectral sky brightness measurements in multiple bands rather than single broadband measurements provide data needed to assess impacts across different wavelength ranges. These metrics offer better tools for regulation, but adoption remains limited. Most cities lack equipment for spectral measurements. Most lighting engineers work with traditional photopic metrics. Most ordinances reference standards developed for pre-LED lighting. The broader lesson concerns the difficulty of predicting environmental impacts of new technologies. LED lighting promised to solve light pollution through energy efficiency. The technology delivered on energy efficiency. But the transition changed the problem rather than solving it, shifting light pollution from primarily yellow wavelengths to blue wavelengths, from a problem satellites could track accurately to one requiring ground-based spectral analysis, from impacts captured by existing metrics to effects requiring new measurement frameworks. We underestimated the complexity of the system we were intervening in. Similar patterns appear across environmental challenges. Solutions designed for one set of metrics create unforeseen problems along unmeasured dimensions. The measurement tools we develop shape which problems we can recognize, and therefore which solutions we attempt. The debate between satellite and ground-based measurements continues because both capture real but incomplete aspects of a complex phenomenon. Satellites provide unmatched geographic coverage and temporal consistency. Ground measurements provide spectral detail and biological relevance satellites cannot match. Neither alone tells the complete story. Together, they reveal that light pollution is not a single problem with a single metric, but a multidimensional environmental transformation affecting astronomical observations, ecological systems, human health, and cultural heritage in distinct ways that require different measurement approaches and different solutions. The question is not which method is correct, but how we integrate multiple measurement frameworks into coherent policy that addresses all dimensions of the problem simultaneously. The rebound effect reveals a counterintuitive truth about technological efficiency that extends far beyond lighting into nearly every domain of human resource use. When we make something cheaper or more efficient, we do not necessarily use less of it. We use more. This principle, first articulated by economist William Stanley Jevons in 1865 regarding coal consumption, states that improvements in efficiency can paradoxically increase total consumption rather than decrease it. Jevons observed that as steam engines became more fuel efficient during the Industrial Revolution, Britain's total coal consumption increased rather than decreased. More efficient engines made steam power economically viable for new applications, expanding the market faster than efficiency-reduced fuel use per application. The same dynamic appears with LED lighting. Better efficiency makes lighting cheaper, and cheaper lighting encourages more total illumination. This seems backwards because we intuitively expect efficiency gains to translate directly into resource savings. If a new streetlight uses half the energy of the old one while providing the same illumination, surely we will use half as much electricity for street lighting. But cities do not maintain constant illumination. They increase it. The money saved on electricity for existing lights funds additional lights in previously unlit areas, brighter lights on major thoroughfares, decorative lighting on buildings and bridges, extended operating hours for sports facilities and parking lots. A city that once operated 10,000 streetlights at 100 watts each, consuming 1 megawatt total, might replace them with LED lights using 50 watts each. Total consumption drops to 500 kilowatts. But then the city installs 5,000 additional lights in parks, residential streets, and pedestrian areas that were previously dark. Total consumption returns to 750 kilowatts, 25% below the original level, but 50% higher than the theoretical minimum. The city declares victory for energy efficiency, while light pollution increases by 50%. Data from cities worldwide confirms this pattern with depressing consistency. A comprehensive analysis published in 2020 by Alejandro Sanchez de Miguel and colleagues examined satellite measurements of 112 cities that underwent LED streetlight conversions between 2014 and 2019. The study compared pre-conversion and post-conversion radiance measurements, accounting for differences in sensor spectral response and atmospheric conditions. The researchers found that while per-fixture energy consumption decreased by an average of 40 to 60%, total upward radiance decreased by only 0 to 15%. Some cities showed slight increases in total radiance despite LED adoption. The gap between per-fixture savings and total emissions savings indicates that cities increased the number or intensity of lights to partially offset efficiency gains. The economic logic behind this behavior is straightforward. Municipal lighting budgets are set based on current operating costs and political priorities around public safety, economic development, and quality of life. When LED conversion reduces operating costs, the budget does not shrink proportionally. The savings stay within the lighting department or get redirected to lighting projects that previously seemed too expensive. City councils view lighting as a public good with no obvious saturation point. More light appears to mean better visibility, enhanced safety, increased economic activity, and improved civic pride. With LED technology making additional lighting affordable, cities install it. The technology that should have solved light pollution instead enabled its expansion into areas that were previously too expensive to illuminate. Think of it as a farmer who installs irrigation technology that cuts water use per acre in half. If the farmer maintains the same acreage, total water consumption drops 50%. But if the farmer instead doubles the irrigated acreage using the money saved on water costs, total consumption stays constant while production increases. From the farmer's perspective, this represents rational economic optimization. From the water resource perspective, efficiency accomplished nothing except enabling expanded extraction. Light pollution follows identical logic. Efficiency gains get reinvested into expanded lighting rather than translated into environmental benefits. The phenomenon extends beyond municipal lighting into commercial and residential sectors. LED strip lights, virtually unknown before 2010, now illuminate millions of homes, businesses, and vehicles. Their low cost and energy efficiency make decorative lighting economically viable for applications where it would have been prohibitively expensive using incandescent bulbs. Businesses outline entire buildings with LED lights, creating architectural illumination that operates all night. Homeowners install landscape lighting, pathway lights, and decorative features that remain lit until dawn. Vehicle underglow, LED signs, and electronic billboards proliferate. Each individual installation uses less energy than the equivalent incandescent lighting would require. Collectively, they add millions of new light sources that did not exist in the pre-LED era. Total light emissions increase even as per-device energy consumption decreases. Observational evidence demonstrates this expansion in remarkable detail. Time series satellite imagery from the COIR's day-night band allows researchers to track how individual cities evolve over years. Madrid provides a particularly well-documented case study. Between 2012 and 2018, Madrid converted approximately 225,000 streetlights from high-pressure sodium to LED, one of the world's largest and most carefully planned conversions. City officials selected 2700 Kelvin warm white LEDs specifically to minimize blue light emissions and circadian disruption, demonstrating unusual awareness of light pollution concerns. The conversion reduced streetlight energy consumption by approximately 44%, saving the city roughly €30 million in 5 years. Satellite measurements showed that while upward radiance in the yellow band decreased as expected, total radiance decreased only marginally, about 2 to 3%, far less than the energy savings would suggest. Ground-based measurements told a more complex story. Researchers measured zenith sky brightness at multiple locations around Madrid using calibrated photometers before and after the LED conversion. Central Madrid showed sky brightness increases of approximately 10 to 15% in blue wavelengths and 5 to 8% in total luminance. Suburban areas showed smaller increases. Rural areas 60 to 100 kilometers from the city center showed virtually no change, suggesting the LED conversion did not significantly expand Madrid's light dome radius, but did increase intensity within already affected zones. The pattern indicated that while Madrid's LED selection minimized some negative impacts through careful spectral control, the city simultaneously increased total lighting enough to offset most of the intended light pollution reductions. Computer simulations predicted this outcome but were largely ignored during planning phases. Atmospheric radiative transfer models simulating Madrid's LED conversion, published in 2016 before the conversion completed, predicted that zenith sky brightness would decrease by only 5 to 10%, despite 44% energy reductions. The models incorporated realistic assumptions about rebound effects, spectral distribution of LED lights, and typical patterns of lighting expansion in growing cities. The simulations accurately forecast what would happen. City officials proceeded with the conversion anyway, emphasizing energy savings and operational improvements rather than light pollution reduction. The case illustrates how economic and operational considerations consistently outweigh environmental concerns in municipal lighting decisions, even when decision-makers have access to accurate, predictive models. The statistical improbability of reversing this trend becomes clear when examining demographic and economic projections. The United Nations projects global population will reach 9.7 billion by 2050, with 90% of growth occurring in urban areas. The global urban population will increase from 4.4 billion in 2020 to approximately 6.7 billion by 2050. Virtually all of this urban growth happens in Africa, Asia, and South America, regions where outdoor lighting infrastructure remains underdeveloped compared to North America and Europe. As these regions urbanize and their economies grow, they will install hundreds of millions of new streetlights, building lights, and commercial illumination. Even if every new installation uses state-of-the-art LED technology and follows best practices for minimizing light pollution, the sheer number of new sources will increase global light emissions dramatically. Economic development correlates almost perfectly with increased lighting. Countries with GDP per capita below $5,000 typically show nighttime radiance levels, orders of magnitude lower than countries with GDP above $20,000. As developing nations increase per capita GDP, their nighttime radiance increases proportionally. China's experience demonstrates this trajectory clearly. Between 1992 and 2012, China's GDP per capita increased from roughly $900 to $6,000. Over the same period, satellite measurements showed China's total nighttime radiance increased by more than 400%. Coastal cities like Shanghai and Shenzhen transformed from moderately lit to among the brightest cities on Earth. The pattern continues across Southeast Asia, India, Africa, and South America. Economic development produces light emissions as reliably as it produces carbon emissions, and for similar reasons. Both represent expanded energy consumption transforming the environment. This ecological framework suggests radically different approaches to outdoor lighting. Instead of asking how much light we can afford to install given energy costs, we ask how little light we can use while achieving essential objectives. Adaptive lighting systems that dim or turn off when no pedestrians or vehicles are present reduce light emissions by 50 to 70% compared to constant illumination, while maintaining safety during actual use. Warmer color temperatures below 3000 years. Kelvin minimize circadian disruption and sky glow, even if they provide slightly lower photopic visibility. Fully shielded fixtures that direct zero light above the horizontal plane eliminate direct upward emissions while often improving ground illumination efficiency. Limiting operating hours, turning off decorative and advertising lights after midnight, reduces impacts during the portion of night when most people sleep and nocturnal ecosystems function most actively. Some communities have begun implementing these approaches with measurable results. Flagstaff, Arizona, has maintained dark sky ordinances since the due to proximity to Lowell Observatory. The ordinances require fully shielded outdoor fixtures, limit light intensity per area, and prohibit certain types of decorative lighting. Satellite measurements show Flagstaff produces approximately 1/3 the upward radiance per capita compared to similarly sized Arizona cities without dark sky protections. Ground-based sky brightness measurements confirm that Flagstaff maintains substantially darker skies, despite being a modern city with full street lighting and commercial development. The existence proof is clear. Cities can provide adequate lighting for safety and commerce, while preserving reasonably dark skies through careful regulation and public commitment to the goal. Modified theories of how light should function in human settlements draw on historical precedent and biological understanding. For most of human history, artificial light was precious and expensive. People used it sparingly and strategically, illuminating specific tasks and spaces while accepting darkness elsewhere. This created a rich variation between light and dark, between public illuminated zones and private dark spaces, between active lit hours and quiet dark hours. Modern all-night uniform illumination eliminates this variation, creating environments that lack the temporal and spatial structure humans evolved within. Some architects and urban planners advocate for recovering some of this variation through lighting design that emphasizes contrast and specificity rather than uniform brightness. The physiological argument supports this approach. Human circadian systems require both light and darkness to function correctly. Exposure to bright light during the day, particularly blue wavelength light, helps set circadian timing and supports alertness and mood. Darkness at night allows melatonin production and triggers physiological processes associated with sleep and recovery. Modern indoor environments often provide insufficient light during the day and excessive light at night, inverting the natural pattern. Outdoor lighting compounds the problem by extending light exposure throughout the night. A lighting strategy optimized for human health would maximize daytime light exposure and minimize nighttime light exposure, the opposite of current trends toward dimmer daytime office lighting and brighter nighttime outdoor lighting driven by energy efficiency and security concerns. The cultural dimension reveals perhaps the deepest counterintuitive aspect. we have come to fear darkness in ways our ancestors did not. Traditional societies lived with dark nights as normal and unremarkable. Darkness brought rest, quiet, and different activities than daylight hours. It was familiar, not threatening. Modern urban dwellers experience darkness as abnormal and potentially dangerous, a condition to be eliminated through lighting. This cultural shift makes light pollution a self-reinforcing phenomenon. Fear of darkness drives demand for more light. More light increases unfamiliarity with darkness. Unfamiliarity breeds greater fear. The cycle continues until darkness becomes so rare that experiencing it triggers genuine anxiety in people who have lived their entire lives in perpetually lit environments. Breaking this cycle requires not just technological solutions, but cultural transformation. People must learn or relearn that darkness can be safe, that appropriate lighting serves specific purposes rather than eliminating darkness entirely, that preserving dark skies offers value worth the modest costs and inconveniences of restraint. This cultural shift faces enormous resistance because it challenges deep-seated assumptions about progress, safety, and quality of life. Yet without cultural change, technological improvements in lighting efficiency will continue producing paradoxical results, each advance enabling expanded illumination that negates the environmental benefits we expect. The problem is not the technology. The problem is what we choose to do with it. The instruments that reveal this transformation operate on principles more sophisticated than simply measuring brightness. A basic LGHT meter, the kind photographers use, detects total luminance within its field of view and reports a number. Sky quality meters advance beyond this by incorporating specific spectral filters and calibrated sensors that convert detected photons into standardized astronomical magnitude units. The Unihedron Sky Quality Meter, introduced in 2005 and now the most widely used device for citizen science light pollution monitoring, contains a TEOS TSL237 light-to-frequency converter sensor covered by a Hoya CM500 infrared blocking filter. The sensor's spectral response peaks near 540 nanometers and spans roughly 400 to 700 nanometers, approximating human photopic vision. A precisely designed wide-angle diffuser limits the field of view to approximately 80 degrees, sampling a large portion of the sky while excluding the horizon where light pollution peaks. The device converts photon flux into frequency, generating more pulses per second as light intensity increases. Internal electronics count these pulses over a precise time interval and convert the count to magnitudes per square arc second using a logarithmic calibration curve established through comparison with laboratory standards. Point the meter at the zenith on a moonless night, press the button, and roughly 5 seconds later it displays a number. A reading of 21.5 indicates excellent dark sky, where the Milky Way appears spectacular and thousands of stars are visible. A reading of 19.0 indicates moderate light pollution, where the Milky Way remains visible but faint. A reading of 17.0 indicates severe light pollution, where only the brightest stars penetrate the sky glow. Each 1 magnitude decrease represents an increase in sky brightness by approximately 2.5 times, following the logarithmic magnitude scale astronomers have used for centuries. Professional astronomical photometers achieve far greater precision and spectral coverage. The Johnson-Cousins photometric system, established by Harold Johnson and refined by Alan Cousins in the EXE, defines standard filter bands that isolate specific wavelength ranges. The U-band covers ultraviolet wavelengths from 300 to 400 nanometers. The B-band covers blue wavelengths from 380 to 480 nanometers. The V-band covers visual wavelengths from 480 to 600 nanometers. The R band covers red wavelengths from 550 to 750 nanometers. The I band covers near-infrared wavelengths from 700 to 900 nanometers. Astronomical photometers equipped with these filters can measure sky brightness separately in each band, revealing how light pollution's spectral distribution changes with different lighting technologies, atmospheric conditions, and viewing directions. The measurements reveal characteristic scales that vary systematically with distance from light sources and atmospheric conditions. In exceptionally dark locations more than 300 kilometers from any significant urban area. Natural sky brightness at the zenith measures approximately 22.0 magnitudes per square arc-second in the V band. This natural background combines contributions from several sources. Starlight from individual stars too faint to resolve contributes approximately 23.5 magnitudes per square arc-second. Integrated starlight from the Milky Way adds roughly 22.7 magnitudes per square arc-second. Zodiacal light, sunlight scattered by interplanetary dust, contributes approximately 23.3 magnitudes per square arc-second, depending on viewing direction and time of year. Airglow, light emitted by chemical reactions in Earth's upper atmosphere at altitudes of 80 to 100 kilometers, varies between 21.5 and 22.5 magnitudes per square arc-second, depending on solar activity and seasonal factors. These components sum to produce the natural baseline against which artificial light pollution appears. Airglow deserves particular attention because it represents a lower limit on sky darkness even in the complete absence of artificial light. Unlike light pollution, which scatters in the lower atmosphere, airglow originates in the upper atmosphere where ultraviolet radiation from the sun ionizes atoms and molecules during the day. At night, these ions recombine, releasing photons in specific wavelength bands. Oxygen atoms produce green light at 557.7 nanometers and red light at 630.0 nanometers. Sodium atoms produce yellow light at 589.3 nanometers. Hydroxyl molecules produce multiple near-infrared emission lines. The total airglow brightness varies by a factor of 2 or more, depending on solar activity, with brighter airglow during solar maximum and following geomagnetic storms. On the brightest airglow nights, natural sky brightness can reach 21.5 magnitudes per square arc-second, dim enough to preserve excellent astronomical observing, but bright enough to set a fundamental limit on darkness. This natural baseline establishes the 0 point from which light pollution measurements diverge. At the edge of a small town with a few thousand residents, 50 kilometers from any larger city, sky brightness typically measures around 20.5 to 21.0 magnitudes per square arc-second, roughly 2 to 3 times brighter than natural conditions. The Milky Way remains clearly visible, prominent enough to cast faint shadows on very dark nights. At the edge of a medium city with 100,000 residents, sky brightness measures approximately 19.0 to 19.5 magnitudes per square arc-second, roughly 6 to 8 times natural brightness. The Milky Way appears as a faint band visible only to observers who know where to look. In suburban areas 20 to 30 kilometers from a major metropolitan center, sky brightness reaches 18.0 to 18.5 magnitudes per square arc-second, 20 to 30 times natural brightness. The Milky Way becomes invisible and only the brightest few hundred stars remain visible. Independent confirmation of these measurements comes from multiple approaches that validate the basic patterns while revealing subtle disagreements instructive for understanding measurement uncertainties. The Globe at Night Citizen Science Program, coordinated by the National Optical Astronomy Observatory since 2006, collects observations from thousands of participants who estimate naked eye limiting magnitude by comparing the visible sky to standard star charts. Between 2006 and 2020, the program gathered more than 200,000 observations from 180 countries. Statistical analysis of this data shows close agreement with sky quality meter measurements, typically within 0.3 magnitudes, despite the subjective nature of naked eye estimates. The agreement confirms that simple instruments and citizen observations can produce scientifically useful data when aggregated across many observers and locations. Satellite measurements provide independent validation at larger scales. The correlation between ground-based sky brightness and satellite-measured upward radiance follows predictable patterns derived from atmospheric physics. Locations measuring 21.0 magnitudes per square arc-second on the ground typically show VIR's nighttime radiance values near 0.5 nanowatts per square centimeter per steradian. Locations measuring 19.0 magnitudes per square arc-second show radiance near 5 nanowatts per square centimeter per steradian. Locations measuring 17.0 magnitudes per square arc-second show radiance exceeding 50 nanowatts per square centimeter per steradian. The logarithmic relationship between ground brightness and satellite radiance reflects the complex interplay of light scattering, atmospheric transmission, and sensor spectral response, but the correlation is strong enough to allow satellite data to predict ground sky brightness with uncertainties typically below 20%. Recent technological advances have dramatically improved measurement capabilities. The International Space Station deployed the NightPod camera stabilization system in 2011, allowing astronauts to photograph Earth at night using commercial digital SLR cameras with exposures long enough to reveal fine spatial detail in city lighting patterns. These photographs, taken from ISS altitude of approximately 400 kilometers, show individual streetlights, building illumination, and stadium lighting with resolution better than 5 meters. Astronauts have captured thousands of nighttime Earth images, creating an archive documenting how specific cities have evolved over the decades since NightPod deployment. Comparison between images from 2012 and 2022 shows LED conversion in city after city, visible as shifts from yellow-orange to blue-white light. The Cities at Night project, founded in 2014 by Alejandro Sanchez de Miguel, processes these astronaut photographs to extract quantitative information about light pollution's spectral characteristics. The project analyzes color ratios in the images, comparing blue, green, and red channels to determine the spectral distribution of city lighting. High blue to green ratios indicate LED or metal halide lighting. High red to green ratios indicate high-pressure sodium lighting. By tracking how these ratios change over time for individual cities, researchers can monitor LED adoption rates and predict resulting changes in sky brightness and circadian impact. The technique provides spectral information that satellite sensors cannot capture, filling a critical gap in global light pollution monitoring. Ground-based all-sky cameras represent another major advance in measurement technology. These systems use fisheye lenses to photograph the entire sky hemisphere from horizon to horizon in a single exposure. Calibrated cameras record the full sky brightness distribution, revealing not just zenith measurements but how brightness varies with altitude and azimuth. This allows researchers to trace light pollution back to specific source regions, determining which cities and which portions of cities contribute most to sky brightness at any location. The European Union funded installation of more than 50 all-sky cameras across Europe between 2015 and 2020 as part of the Stars for All project. The network provides continuous monitoring of sky brightness changes across the continent, detecting both gradual trends and sudden changes from new lighting installations or policy modifications. Spectroscopic measurements of sky brightness extract even more detailed information about light pollution sources. A spectrograph disperses light into its component wavelengths, allowing measurement of brightness at hundreds or thousands of distinct wavelengths simultaneously. This reveals the specific emission lines and spectral features characteristic of different lamp types. High-pressure sodium lamps show strong, narrow emission at 589.3 nanometers. Metal halide lamps show multiple emission lines from mercury at 405, 436, 546, and 578 nanometers. White LEDs show broad continuum emission with a blue peak near 450 nanometers and a yellow-green phosphor emission peak near 550 nanometers. By analyzing sky brightness spectra, researchers can determine the mix of lamp types contributing to light pollution at any location and track how this mix changes as cities adopt new technologies. Precision improvements in recent years have made it possible to detect changes in sky brightness of just a few %, enabling researchers to assess whether dark sky ordinances and lighting modifications produce measurable benefits. The Sky Quality Camera, developed by the Spanish National Research Council and deployed at multiple Spanish observatories starting in 2018, achieves photometric precision better than 0.5 magnitudes through automated calibration against standard stars and sophisticated image processing. This precision allows detection of sky brightness changes corresponding to installation of just a few dozen streetlights in cities 50 to 100 kilometers away. The sensitivity demonstrates that modern instruments can track essentially real-time changes in light pollution, making it possible to attribute changes to specific actions and evaluate policy effectiveness quantitatively. Future observational capabilities will expand understanding further. The Spectrum-1 satellite, scheduled for launch in 2025, will carry the Night Illumination Imager designed specifically for light pollution monitoring. Unlike VOIRs, which measures visible and near-infrared wavelengths in a single broad band, the Night Illumination Imager will measure 4 separate spectral bands spanning blue, green, yellow, and red wavelengths. This will allow discrimination between different light source types from orbit and direct measurement of LED adoption rates globally. The satellite will orbit in a sun-synchronous orbit with crossings at 10:30 p.m. local time, earlier than VIAS's 1:30 a.m. crossing time, capturing light pollution during peak evening hours when emissions are typically brightest. Ground-based networks continue expanding as well. The Loss of the Night Network, coordinated by the German Research Center for Geosciences, aims to deploy automated photometers at 1,000 locations worldwide by 2030, creating unprecedented spatial and temporal coverage of sky brightness changes. The network uses standardized SQM-LE devices that continuously record measurements every minute and upload data to central servers via internet connections. This allows tracking of hourly, daily, seasonal, and annual variations in light pollution, while providing early warning of sudden changes from new lighting installations or policy modifications. The data will enable researchers to test whether global light pollution growth rates are accelerating, stable, or beginning to decline as awareness increases and LED technology enables better lighting control. The transformation manifests differently in different locations, creating a global mosaic of light pollution patterns that reveal how geography, culture, economics, and policy interact to shape the night. Consider Singapore GHT. Consider Singapore, an island city-state measuring just 730 square kilometers, with a population of 5.7 million. Satellite measurements from 2019 showed Singapore as one of the most intensely lit places on Earth, with average nighttime radiance exceeding 200 nanowatts per square centimeter per steradian, roughly 40 times the radiance of moderately lit American suburbs. Ground-based measurements confirmed that 100% of Singapore's population lives under skies measuring 17.0 magnitudes per square arc second or brighter. conditions where fewer than 50 stars remain visible to the naked eye. The Milky Way has been invisible from Singapore since approximately 1970, and an entire generation has grown up without any possibility of seeing it from their homeland. What makes Singapore's case particularly instructive is that this light pollution results not from inefficiency or neglect, but from deliberate policy prioritizing safety, economic activity, and international image. Singapore maintains extensive street lighting throughout the island, with fixtures spaced every 30 to 50 meters on major roads and every 50 to 100 meters on residential streets. Commercial districts remain brightly lit 24 hours daily. The Marina Bay waterfront features elaborate architectural lighting, synchronized to music and video displays, creating nightly light shows visible from space. The government views bright nighttime illumination as essential to Singapore's identity as a modern, prosperous, safe city operating continuously around the clock. Dark sky preservation has never appeared as a policy consideration because Singapore lacks astronomical observatories, has minimal rural area, and exists in a region where light pollution from surrounding Malaysian and Indonesian cities would impact sky darkness regardless of Singapore's actions. Yet Singapore demonstrates that even extreme light pollution proves compatible with economic success and public safety. Crime rates in Singapore remain among the world's lowest, despite or perhaps unrelated to intense illumination. The economy thrives. Citizens report high quality of life. This challenges the assumption that reducing light pollution would necessarily compromise safety or prosperity. Singapore achieves safety through effective policing, strong social cohesion, and comprehensive surveillance, not primarily through bright lighting. The bright lighting serves cultural and aesthetic functions, projecting an image of modernity and vitality rather than practical security needs. Other cities could potentially achieve similar safety outcomes with substantially less illumination by focusing on the actual determinants of safety rather than using light as a proxy. Compare this with Flagstaff, Arizona, a city of 75,000 residents that has maintained dark sky protections since 1958 due to proximity to Lowell Observatory, located just outside city limits. Flagstaff's lighting ordinances require all outdoor fixtures to be fully shielded, directing light downward rather than upward or sideways. The ordinances limit light intensity per area, restrict operating hours for certain types of illumination, and prohibit searchlights and laser displays. These regulations apply citywide, affecting residential, commercial, and industrial properties equally. Satellite measurements from 2019 showed Flagstaff produces approximately 15 nanowatts per square centimeter per steradian, roughly 1/14 the radiance of Singapore and 1/3 the radiance of similar-sized Arizona cities without dark sky ordinances. Ground-based measurements from within Flagstaff typically record sky brightness between 19.5 and 20.0 magnitudes per square arc-second, depending on location and atmospheric conditions. From the darker outskirts and nearby natural areas, observers regularly see sky brightness approaching 21.0 magnitudes per square arc-second, dark enough for the Milky Way to appear prominent and thousands of stars to be visible. Flagstaff demonstrates that a modern city with complete infrastructure, active commercial districts, and growing population can preserve reasonably dark skies through consistent policy maintained over decades. The key factors appear to be strong institutional support from the astronomy community, early adoption of ordinances before extensive development, locked in incompatible lighting, and ongoing public education, creating cultural acceptance of lighting restrictions. The comparison between Singapore and Flagstaff illustrates extremes on a spectrum that includes thousands of intermediate cases. Most cities fall between these poles, with light pollution levels determined by combinations of population density, economic activity, cultural attitudes, geographic setting, and historical development patterns. Cities in Western Europe typically show lower per capita light emissions than American cities of comparable size, reflecting denser urban form, less suburban sprawl, and different attitudes about nighttime illumination. Asian megacities often show extremely high light emissions in core commercial districts, with much darker residential areas, reflecting concentrated economic activity and vertical development patterns. Latin American cities show high variability, with wealthy neighborhoods featuring intense illumination, while poorer areas remain darker due to infrastructure limitations rather than policy choices. Recent discoveries reveal how rapidly light pollution patterns can change when economic conditions shift. The 2008 financial crisis produced measurable decreases in nighttime radiance across Greece, Spain, Italy, and other European nations experiencing severe recessions. Satellite time series showed radiance decreases of 10 to 20% between 2008 and 2013 in the hardest-hit regions, corresponding to reduced commercial activity, decreased public lighting budgets, and widespread energy conservation measures. Syria's civil war, beginning in 2011, caused nighttime radiance to decrease by more than 90% in affected cities as infrastructure was destroyed and populations fled. These tragic events demonstrated that light pollution responds quickly to economic and social conditions, decreasing when human activity decreases and presumably increasing when activity expands. The global COVID-19 pandemic provided an unintended natural experiment in light pollution dynamics. Lockdowns implemented in March and April 2020 across most of the world dramatically reduced economic activity, closed businesses, restricted movement, and altered daily routines for billions of people. Researchers anticipated corresponding decreases in nighttime light emissions as commerce slowed and cities quieted. Satellite measurements showed more complex patterns. Commercial district lighting decreased by 15 to 30% in major cities during strict lockdowns. But residential area lighting often increased as people spent more time at home, working remotely, and using outdoor spaces near residences for recreation under movement restrictions. Overall, nighttime radiance decreased by just 5 to 10% globally during peak lockdown periods, far less than the 40 to 60% decreases in economic activity and vehicular traffic. Ground-based sky brightness measurements revealed even subtler effects. Observers in suburban and rural areas reported that sky brightness decreased noticeably during lockdowns, with some locations showing improvements of 0.2 to 0.4 magnitudes. But observers in urban cores often reported no change or slight increases in sky brightness despite satellite measurements showing decreased upward radiance. The explanation involves spectral shifts and changed atmospheric conditions. With dramatically reduced vehicular traffic, urban air quality improved substantially during lockdowns. Lower aerosol concentrations decreased atmospheric scattering efficiency, partially offsetting the impact of reduced light emissions. Simultaneously, shifts in lighting patterns toward more residential and less commercial use changed the spectral distribution of urban lighting in ways satellites struggled to capture accurately. The pandemic measurements illustrated how atmospheric conditions interact with light emissions in complex ways that simple models cannot always predict. The statistical distribution of light pollution across Earth's surface reveals stark inequalities in access to dark skies. Analysis of the 2016 World Atlas data showed that approximately 3 billion people, 40% of humanity, live under skies bright enough to prevent seeing the Milky Way. But this population is distributed extremely unevenly geographically. In the United States and European Union, roughly 60 to 70% of the population cannot see the Milky Way. In China, approximately 50% of the population has lost this view. In India, roughly 30% cannot see the Milky Way, though this percentage is increasing rapidly as cities expand and LED lighting spreads. In sub-Saharan Africa, less than 10% of the population lives under skies too bright for the Milky Way to appear, though this may change dramatically over coming decades as urbanization accelerates. The spatial patterns show surprising characteristics. Light pollution does not decrease linearly with distance from cities, but shows rapid initial decline, followed by slow, asymptotic approach to natural darkness. Within 50 kilometers of a major city, sky brightness typically exceeds 19.0 magnitudes per square arc-second. Between 50 and 150 kilometers, brightness decreases to approximately 20.0 to 20.5 magnitudes per square arc-second. Beyond 150 kilometers, brightness approaches natural levels of 21.5 to 22.0 magnitudes per square arc-second if no other cities lie within range. This pattern means that truly dark sky areas require distances of 150 to 300 kilometers from significant urban development. In densely populated regions like the eastern United States, Western Europe, coastal China, and Japan, such distances place dark sky locations beyond reach of most residents without extensive travel. Unexplained aspects of light pollution distribution continue to puzzle researchers. Some cities with comparable population, density, and economic activity show radiance levels differing by factors of 2 or 3 without obvious explanations. Cultural factors likely play roles. Different attitudes about appropriate nighttime illumination across societies, but quantifying these cultural influences proves difficult. Historical development timing also matters. Cities that grew primarily after 1980 during the era of bright sodium vapor and metal halide lighting tend to be brighter than cities that reached mature development before 1970 when lighting was less intense. But exceptions abound. Some older cities upgraded lighting extensively and now appear as bright as newer developments. Some newer cities adopted dark sky principles from the start and remain relatively dark. The complexity suggests multiple factors interact in ways that resist simple categorization. Ongoing research explores biological and ecological thresholds where light pollution transitions from minor disturbance to severe disruption. Laboratory studies establish that many organisms show measurable responses to light levels far below what humans perceive as bright. Insects alter behavior at illuminance levels below 1 lux, equivalent to sky brightness roughly 10 times natural levels. Birds show circadian disruption at levels below 0.3 lux. Plants alter flowering and seasonal timing at light levels barely distinguishable from natural moonlight. These thresholds suggest that ecological impacts begin at much lower light pollution levels than previously assumed. Areas considered relatively dark by human standards, measuring 20.0 to 20.5 magnitudes per square arc-second, may already be bright enough to disrupt sensitive species and alter ecosystem function. Field studies tracking population changes in light-polluted versus dark areas provide mixed evidence. Some studies find clear declines in nocturnal insect abundance, bat activity, and bird breeding success correlated with increasing light pollution. Other studies find no clear relationships, possibly because other factors like habitat quality, food availability, and predation pressure override light pollution effects. The difficulty in isolating light pollution from other anthropogenic impacts complicates establishing causation. Urban areas with severe light pollution also typically have extensive development, fragmented habitat, high noise levels, and altered microclimates. Separating the specific contribution of light pollution to observed ecological changes requires carefully designed studies controlling for confounding variables, studies that remain rare due to logistical challenges and funding limitations. The discovery in 2017 that some organisms may benefit from light pollution added unexpected complexity to the ecological picture. Researchers studying spiders in Swiss cities found that bridge spiders constructed webs near streetlights caught significantly more insects than webs in darker locations, likely because many flying insects are attracted to lights. The spiders feeding on this concentrated prey source showed higher growth rates and reproductive success than dark site spiders. Similarly, some bat species preferentially forage around streetlights where insects aggregate, while other bat species avoid lit areas. These findings suggest light pollution creates ecological winners and losers rather than universally harming all species. Understanding the full ecosystem impacts requires tracking not just individual species responses, but how altered species interactions reshape community structure and ecosystem function. The longest-running continuous light pollution monitoring dataset comes from the McDonald Observatory in West Texas, where automated photometers have recorded sky brightness every night since 1998. The 25-year time series reveals gradual brightening of approximately 0.3 magnitudes per decade in the direction of Midland, Odessa, two cities 90 kilometers northeast of the observatory. But the trend shows substantial year-to-year variability, with brief periods of decreasing brightness followed by rapid increases. The pattern correlates with oil and gas industry activity in the Permian Basin, where natural gas flares and industrial lighting expand during boom periods and contract during busts. The data illustrate how economic cycles drive light pollution changes on timescales from months to years, complicating efforts to detect long-term trends and evaluate policy interventions. Similar long-term datasets from other observatories tell similar stories of inexorable brightening, punctuated by temporary reversals. The Mount Wilson Observatory dataset, extending back to 1973, shows the Los Angeles Light Dome brightening by roughly 1.5 magnitudes over 45 years, a tenfold increase in sky brightness. The Palomar Observatory dataset shows San Diego's Light Dome brightening by approximately 1.0 magnitudes between 1980 and 2020. The McDonald, Mount Wilson, and Palomar datasets collectively document how astronomical observatories, established in remote locations specifically chosen for dark skies, have watched those dark skies deteriorate over decades as distant cities grow and spread. The story these measurements tell is one of slow-motion loss, invisible to casual observation, but undeniable in the accumulated data of nightly measurements spanning decades. The measurements revealing Earth's transformation contain an observational bias so fundamental that it shapes every conclusion we draw about light pollution's severity and significance. We measure light pollution from Earth's surface, from within the phenomenon itself, using instruments designed by humans who live under light-polluted skies. Our perspective is not that of an external observer viewing Earth objectively, but of inhabitants embedded in the system we attempt to measure. This insider perspective affects what we can see, what we think to measure, and how we interpret the results. Consider that every light pollution measurement ever taken originates from a planet experiencing light pollution. We have no comparison with measurements from worlds that deliberately chose different paths, that developed advanced civilization while preserving natural darkness, or that never developed artificial lighting at all. This creates a peculiar epistemic situation. When astronomers measure cosmic microwave background radiation or galactic rotation curves, they observe external phenomena independent of human presence. The measurements would remain the same regardless of whether humans existed to take them. But light pollution is intrinsically anthropogenic, existing only because we create it, measurable only from locations where we live, significant only relative to our biological needs and cultural values. The phenomenon and its observation are inseparable. We cannot step outside ourselves to measure light pollution objectively. Every measurement reflects choices about what matters, what counts as pollution versus appropriate illumination, which impacts warrant attention versus acceptance as necessary costs of civilization. The bubble concept emerges from recognizing that each observer experiences a personal light pollution environment determined by their specific location and circumstances. Someone living in central Tokyo experiences fundamentally different night sky conditions than someone living in rural Montana, despite both inhabiting the same planet in the same era. The Tokyo resident lives in a bubble of intense light pollution, where the natural night sky has been replaced entirely by artificial sky glow. Their direct sensory experience provides no access to natural darkness. The Montana resident lives in a bubble of relatively preserved darkness with the Milky Way visible most clear nights. Their experience remains closer to what humans experience throughout history. Both bubbles are real. Neither is more valid than the other, but they are mutually incomprehensible without deliberate effort to understand experiences radically different from one's own. This bubble effect extends beyond individual experience to entire regions and cultures. Someone who has lived their entire life in light-polluted urban environments often expresses genuine disbelief when first seeing a truly dark sky. The number of visible stars seems impossible. The three-dimensional structure of the Milky Way appears unreal, like an image projected on the sky rather than light from distant stars. Dark adaptation takes longer than expected because the visual system has never been required to reach full sensitivity before. The experience can be unsettling, even frightening, because it contradicts the internal model of what night should look like, built over decades of life in bright environments. The bubble of light-polluted experience creates perceptual expectations that make natural darkness feel abnormal. The reverse occurs as well, though less commonly documented. People who grow up in areas with dark skies and later move to cities often report persistent discomfort with the perpetual twilight of urban nights. The constant low-level illumination prevents full darkness, disrupting sleep and creating a vague sense that something is wrong, though they may struggle to articulate what. The loss of the night sky creates a psychological void not easily filled by urban amenities. Some adapt and eventually forget what they lost. Others never adjust, maintaining permanent awareness that they live in environments fundamentally disconnected from natural cycles. These individual experiences aggregate into cultural differences where entire populations normalize radically different relationships with darkness and the night sky. How perspective affects measurements becomes quantitatively important when comparing light pollution across locations and times. Sky brightness measurements depend critically on atmospheric conditions, which vary with weather, season, and local geography. A coastal city with frequent marine layer clouds shows different light pollution characteristics than an inland city with clear, dry air, even with identical ground lighting. The clouds increase scattering and can make sky brightness worse, but they also block starlight and the Milky Way, making the absolute loss of astronomical visibility potentially less severe than in clear locations. Which effect dominates depends on measurement methodology and what aspects of light pollution concern the observer most. Temporal perspective similarly shapes conclusions. Measurements taken over months or years reveal seasonal patterns, variations in humidity and aerosol content, changes in vegetation that affect ground albedo, and slow trends from gradual lighting increases or policy modifications. Measurements taken over days or weeks might show only weather-related variations and miss longer-term trends. The temporal scale of observation determines which changes appear significant and which vanish into noise. A researcher measuring sky brightness for 2 weeks might conclude conditions are stable, while a decade-long dataset from the same location reveals continuous degradation. The phenomenon exists on multiple timescales simultaneously, and our access to it depends on how long and how carefully we look. The typicality question poses deeper challenges. Is Earth's experience of rapid light pollution growth typical of how technological civilizations develop? Or are we unusual in the speed and totality of our transformation of the night? We cannot answer this directly because we have no other technological civilizations to observe. But we can examine our own history and ask whether the current trajectory was inevitable given human nature and technology, or whether alternative paths existed and potentially still exist. The historical record suggests both inevitability and contingency. Electric lighting, once invented, spread rapidly because it provided genuine benefits for safety, productivity, and quality of life. This appears nearly inevitable given human preferences for extending useful time beyond daylight hours. But the specific forms lighting took, the intensity levels considered normal, the willingness to tolerate upward light waste, the adoption of technologies that maximize atmospheric scattering, these aspects appear more contingent. Japan, despite being wealthy and technologically advanced, maintained more restrained outdoor lighting than the United States through the ease, suggesting cultural factors shape lighting choices beyond simple availability. The Netherlands implemented extensive motion sensor adaptive street lighting in that reduces emissions by more than 50% compared to constant illumination while maintaining safety. These examples demonstrate that societies can make different choices about lighting even at comparable development levels. Our specific pattern of light pollution is not inevitable but reflects particular cultural, economic, and policy decisions that could have been different. The cosmological principle at stake here is not the traditional cosmological principle, that the universe appears roughly the same from all locations and has no special center. Rather, it is the anthropological principle that our experience as humans on Earth represents a typical example of how intelligent technological species experience the universe. If our rapid transformation of the night sky through light pollution is typical, then perhaps intelligent observers anywhere eventually create similar conditions, making natural dark skies a temporary phase in the evolution of technological civilizations. If our experience is atypical, perhaps shaped by specific choices we could have made differently, then other civilizations might develop while preserving their access to natural darkness. This connects directly to the Copernican principle, the insight that Earth does not occupy a special position in the cosmos. Copernicus demonstrated that Earth orbits the Sun rather than vice versa, displacing Earth from the center of the universe. Subsequent discoveries reinforced this principle. The Sun is an ordinary star in an ordinary galaxy. Our galaxy is an unremarkable member of the local galactic cluster. Nothing about our cosmic location appears special or privileged. The Copernican principle suggests we should be skeptical of claims that Earth occupies a unique position or that human experience differs fundamentally from what other observers elsewhere would experience. If we accept this principle, then our rapid development of severe light pollution suggests this pattern may be typical rather than exceptional. But here is where the argument becomes uncomfortable. The Copernican principle works well for physics and cosmology, domains where the laws of nature apply universally. It may not extend reliably to cultural and technological development, which involve choices, values, and historical contingencies that could play out differently in different contexts. Other intelligent species might value darkness more than humans appear to. They might develop technologies that provide illumination without scattering light into the atmosphere. They might implement cultural practices that limit nighttime lighting regardless of technological capability. Or they might, like us, prioritize immediate benefits of extensive lighting over preservation of natural darkness. We cannot know without additional examples. Anthropic considerations complicate this further. The anthropic principle observes that the universe must be compatible with the existence of observers, otherwise no one would be present to observe it. Applied to light pollution, we might note that any civilization capable of measuring light pollution has already developed artificial lighting technology, ensuring that light pollution exists to some degree. We cannot observe civilizations that never developed artificial light because they would lack the technology to make the observations we consider. This observation selection effect means our sample of technological civilizations, currently one, is biased toward those that create light pollution. We might be typical of observable civilizations, even if most civilizations overall develop differently. Future surveys will test these ideas by determining whether light pollution growth rates are accelerating, stabilizing, or beginning to decline as awareness increases. The Spectrum-1 satellite, scheduled for 2025 launch, will provide spectral data allowing precise tracking of LED adoption and changes in blue light emissions. If blue light emissions decrease over the next decade as cities adopt warmer LEDs in response to health concerns, this would suggest that human societies can respond to light pollution awareness and modify their trajectory. If blue light emissions continue increasing despite widespread awareness of the problems, this would suggest the economic and cultural factors driving light pollution growth override environmental and health considerations. Ground-based monitoring networks will track local and regional changes with precision impossible from satellites. The loss of the night. Networks planned 1,000 automated monitoring stations will detect lighting changes from individual developments, allowing researchers to correlate light pollution trends with specific policies, economic conditions, and cultural movements. If cities implementing dark sky ordinances show measurably slower growth in light pollution than comparable cities without such policies, this provides evidence that deliberate action makes a difference. If policy differences produce no measurable impact, this suggests the problem transcends what local regulations can address. As a natural laboratory, Earth's light pollution offers unprecedented opportunity to study how human activities transform planetary environments and how societies respond when these transformations create recognizable problems. The case differs from climate change, which involves century-scale delays between cause and effect, or biodiversity loss, which occurs gradually and often invisibly. Light pollution appears immediately. Turn on lights and the sky brightens. Turn them off and darkness returns within hours as scattered light dissipates. This near instantaneous response allows testing interventions and observing results in timeframes compatible with human decision cycles and scientific studies. If we cannot solve light pollution, a problem where cause and effect are clear and immediate, where solutions are technically straightforward and economically viable, what does this suggest about our ability to address slower, more complex environmental challenges? The answer emerging from decades of light pollution research is nuanced and somewhat troubling. We can solve light pollution in specific locations through dedicated effort and maintained commitment. Flagstaff proves this. Dark sky reserves demonstrate it. Individual cities show measurable improvements when they prioritize the goal. But globally, light pollution continues accelerating despite this knowledge and these examples. The benefits of additional lighting, both real and perceived, consistently outweigh concerns about light pollution in the economic and political calculations that determine development patterns. We possess the knowledge and technology to preserve dark skies. We lack the collective will to prioritize this goal above other objectives. This pattern suggests our experience of light pollution may indeed be typical of how technological civilizations develop. The immediate benefits of extending useful time through artificial lighting prove overwhelmingly attractive to societies with the technology to achieve it. The costs of light pollution, ecological disruption, health impacts, loss of cultural heritage appear abstract and distant compared to tangible benefits of brightly lit streets and buildings. Even when costs become measurable and evidence accumulates, changing course requires collective action that proves difficult to coordinate across millions of independent actors making individual lighting decisions. The tragedy of the commons, where rational individual choices produce harmful collective outcomes, appears to be a fundamental feature of how intelligent species interact with their environments. If this is correct, then the night sky we have lost may represent a casualty of inevitable developmental pressures rather than a reversible mistake. Not because reversing the loss is technologically impossible, but because the social, economic, and political conditions that would enable reversal appear not to arise reliably in technological civilizations. We are capable of preserving darkness. We are not apparently the kind of species that prioritizes doing so when other options remain. This is not a limitation of technology or knowledge. It is a limitation of collective decision-making in the face of competing values and distributed causality. The question for future generations becomes whether this limitation is permanent, or whether awareness, education, and shifting values might eventually produce different outcomes. We live at a unique moment, the transition period where light pollution has become severe enough to recognize as a problem, but not so long established that alternatives seem impossible. The choices made over the next few decades, whether cities adopt better lighting practices, whether regulations evolve to address new technologies, whether public awareness translates into political will determine whether our current trajectory represents the unavoidable path of technological development or just one possible route among many. The measurements we take now will tell future observers which path we chose, documenting either the loss of Earth's night sky or its gradual restoration, a record written in nightly sky brightness readings extending across decades and eventually centuries.